Welcome to the Late Lab. It's wonderful to have you here. Before settling in, let curiosity wander for a moment. Where are you watching from tonight? Tucked under the covers with the lights low? Resting on the sofa after a long day? Half listening on a quiet evening while the world outside slowly winds down? Wherever you happen to be, hopefully you're comfortable, unhurried, and ready to let your thoughts drift somewhere strange but gentle. If you enjoy calm little journeys through science, a like and subscribe really does help the channel more than you might think. And if you're already here often, thank you. Truly, it means a great deal, and it helps keep this small, sleepy corner of the internet glowing. Now, tonight's subject may not sound especially restful at first. Quantum physics has a reputation for being slippery, baffling, and occasionally rude to common sense. But taken slowly, it becomes less like a wall of impossible ideas and more like a quiet invitation to look underneath the surface of everything. So let's begin nice and gently. What is quantum physics? And why does the ordinary world seem to be built from rules that feel anything but ordinary? There is a small strangeness hidden inside every ordinary beam of light. It is there in the soft glow of a bedside lamp, in the orange warmth of a candle flame, in the colour of the sky just before night takes over, and in the gentle heat that rises from a cup of tea when it has been forgotten for slightly too long. At first, none of this seems especially mysterious. Light arrives, things glow, warm objects cool down, and the world carries on with its usual quiet confidence. A room brightens when a switch is pressed. A metal poker changes colour in a fire. Sunlight passes through a window and lands across the floor as if that is the most natural thing in existence. And for a long time, science seemed to understand most of this beautifully. By the late 19th century, physics looked almost complete. Not finished in every tiny detail, of course, because science has never been quite that tidy, but complete enough that many of its deepest foundations seemed secure. Isaac Newton's laws of motion had explained the fall of apples, the swing of pendulums, the path of cannonballs, and the graceful motion of planets around the sun. James Clerk Maxwell had brought electricity, magnetism, and light together into one magnificent theory, showing that light itself could be understood as an electromagnetic wave. Thermodynamics had explained heat, work, engines, pressure, temperature, and the slow, unavoidable drift of energy from useful order into less useful disorder. It was an astonishing achievement. The universe, once full of mysterious forces and hidden causes, had begun to look like a vast, elegant machine. If the position and motion of every part could somehow be known, perhaps the future might unfold from the past with perfect precision. Reality seemed continuous, smooth, and predictable. Energy could be passed from one object to another in any amount. Waves could rise and fall with any height. A moving object could travel at any speed allowed by its circumstances. Nature did not seem to step. It flowed. But there were small problems. Not loud problems, at least not at first. No planets were suddenly flying off into space in protest. No teacups were levitating in laboratories, which would certainly have made the paperwork more interesting. The problems were quieter than that. They appeared in careful measurements, in heated objects, in the colours of atoms, and in the question of exactly how matter gives off and absorbs light. One of the most important of these problems involved heat radiation. Every object with a temperature gives off electromagnetic radiation. A person gives off infrared radiation. A warm stove does too. A piece of iron heated in a forge first glows dull red, then brighter orange, then yellow-white if it becomes hot enough. The hotter something becomes, the more energy it emits, and the shorter the wavelengths of the strongest radiation become. This is why colour and temperature are linked. A red-hot object is cooler than a white-hot object. A blue-white star is hotter at its surface than a red star. The universe, rather helpfully, colour-codes some of its furnaces. Physicists study this using an idealized object called a black body. A black body is not necessarily black in the everyday sense. It is a perfect absorber and emitter of radiation, a simplified object that takes in all the radiation falling on it and gives off radiation according only to its temperature. Real objects can come close to this behaviour, and laboratory devices can be built to approximate it very well. The advantage of a black body is that it removes messy details like surface texture, chemical composition, and reflectivity. It lets the question become wonderfully clean. What kind of light should a hot object emit at a given temperature? Classical physics had an answer. Unfortunately, the answer was wrong. When physicists used the best classical ideas available, the prediction worked reasonably well for some wavelengths, but failed disastrously at short wavelengths. The theory suggested that a hot black body should emit more and more energy at higher and higher frequencies, especially in the ultraviolet region and beyond. In plain language, the calculation implied that heated objects should pour out impossible amounts of high-frequency radiation. This was later called the ultraviolet catastrophe, a name that sounds slightly dramatic until one remembers that physics does enjoy a good catastrophe when the mathematics misbehaves. The real world did not do this. Hot objects emitted radiation in a measured, orderly pattern. Their intensity rose, reached a peak, and then fell away at shorter wavelengths. The curve was smooth, reliable, and repeatedly confirmed. Nature had no interest in the runaway disaster predicted by classical theory. Something in the old picture was missing. Into this problem stepped Max Planck. In 1900, Planck was trying to solve the puzzle of black-body radiation. He was not trying to overthrow reality, frighten future students, or make the word quantum famous in documentaries with ominous music. He was trying to find a mathematical rule that matched the experimental data. The solution he discovered was strange. To make the numbers come out correctly, he had to treat energy as if it were not exchanged in a perfectly continuous flow. Instead, the energy of tiny oscillators in the walls of a heated object could only change in small, discrete amounts. These amounts came in packets. That was the beginning of the quantum. The word quantum simply means a discrete quantity, a specific amount rather than any amount at all. In this setting, it meant that energy could be absorbed or emitted in little units, rather than divided endlessly into a perfectly smooth stream. Planck did not initially treat this as a sweeping statement about the true nature of the universe. It was at first a clever and reluctant mathematical move, but it worked. It matched the black body radiation curve. It removed the ultraviolet catastrophe. It suggested that beneath the smooth glow of ordinary heat, nature might be counting in tiny steps. That idea was deeply unsettling because it cut against the grain of classical physics. In the older view, energy was like water flowing down a channel, able to rise or fall continuously. Planck's result hinted that, at the smaller scales, energy was more like coins being exchanged in set denominations. Not coins one could hold, of course, and not little golden tokens rattling around inside atoms, charming though that image may be. The point was subtler. Nature seemed to restrict certain exchanges of energy to definite amounts, and once that door opened, it did not close again. The mystery of black-body radiation was not just a technical problem about hot objects. It was a sign that the everyday world, with all its apparent smoothness, is built from rules that become unfamiliar when examined closely enough. Light can behave like a wave, spreading and interfering. Energy can arrive in packets. Atoms can emit precise colours. Matter can seem solid and continuous, while depending on tiny structures that obey rules nothing like ordinary intuition. This is why quantum physics can feel so strange. Not because it is vague or mystical, or an invitation to make things up with a serious expression. Quantum physics is strange because it is precise. It grew from experiments that refused to fit the older theories. It survived because its predictions matched reality with extraordinary accuracy. Again and again, nature seemed to say that the world beneath familiar experience was not less orderly than expected, but ordered in a different language. And perhaps that is the gentlest way to begin. Quantum physics does not start by asking anyone to abandon the ordinary world. It starts with the ordinary world itself, with warmth, with colour, with a glowing object in a dark room, with the simple fact that light from hot matter follows a pattern classical physics could not explain. The strangeness was always there, folded quietly into the glow. The problem with hot objects was not that they glowed. That part was familiar enough. A coal in a fire, a heated iron bar, the filament of an old light bulb, and the surface of a star all announce their temperature through light. Warm things shine mostly in invisible infrared. Hotter things glow red. Hotter still, they brighten toward orange, yellow, white, and eventually blue-white, as if matter itself is slowly learning to sing in higher notes. The real problem was that classical physics could not explain the song. In the 19th century, physicists had developed a powerful way to think about heat and radiation. Heat was connected to the motion of atoms and molecules, even before atoms were accepted with complete confidence by everyone. Light was understood through James Clerk Maxwell's electromagnetic theory, one of the great achievements of physics. According to Maxwell, light was an electromagnetic wave, a self-sustaining ripple of electric and magnetic fields moving through space. Thermodynamics explained the flow of heat and energy with remarkable success. Statistical mechanics, developed by scientists such as Ludwig Boltzmann and James Clerk Maxwell, connected temperature to the restless microscopic motion of matter. Put together, these ideas seemed more than strong enough to handle the glow of a heated object, and yet when physicists tried to calculate the radiation from an ideal black body, something went badly wrong. A black body is a perfect absorber and emitter of radiation. It is a simplified object that absorbs all incoming light and gives off radiation according only to its temperature. In the laboratory, the idea can be closely approximated with a small hole in a heated cavity, because radiation entering the hole is absorbed inside, while radiation coming back out carries the characteristic pattern of the cavity's temperature. That pattern was measured with increasing precision. It was smooth, it was orderly. At each temperature, the radiation rose to a peak at a particular range of wavelengths, then declined again. The peak moved towards shorter wavelengths as the object became hotter. Nothing about the experimental curve looked chaotic or explosive. Nature behaved with elegant restraint, which is always nice when one is heating equipment in a laboratory and hoping it does not become a philosophical incident. Classical theory, however, predicted something impossible. The calculation suggested that a perfect heated object should release more and more energy at shorter and shorter wavelengths. As the radiation moved into the ultraviolet part of the spectrum and then beyond it, the emitted energy should rise without limit. In other words, classical physics predicted that the object should pour out an absurd, infinite amount of high-frequency radiation. This failure became known as the ultraviolet catastrophe. The name sounds dramatic, but the issue was genuinely serious. It was not just a small mismatch between theory and measurement. It was not the sort of error that could be politely hidden under a rug and revisited after tea. The prediction was physically impossible. Objects in the real universe do not radiate infinite energy simply because they are warm. A stove does not become an endless ultraviolet lighthouse. a candle does not quietly destroy physics from the mantelpiece. The ultraviolet catastrophe revealed that something in the classical understanding of energy, matter, and radiation was incomplete. The difficulty came partly from treating energy as if it could be shared continuously among all possible electromagnetic waves inside the heated cavity. Classical reasoning allowed each mode of vibration, each possible standing wave of radiation, to receive energy. At low frequencies, this did not produce a disastrous result, but at high frequencies there were far too many possible modes, and the calculation handed them energy too generously. The result was the runaway prediction. The theory was essentially feeding energy into an unlimited crowd of high-frequency possibilities, and the mathematics had no natural way to stop. Real black-body radiation did have a natural stopping behavior. The curve rose, peaked, and fell. The question was why. Max Planck found the answer, though even he did not immediately treat it as the beginning of a new reality. In 1900, Planck was searching for a formula that matched the observed blackbody spectrum. He had excellent experimental data to explain, especially from work associated with researchers such as Otto Lummer, Ernst Pringsheim, Heinrich Rubens, and Ferdinand Kuhlbaum. The measurements were not vague guesses. They were careful laboratory results showing exactly how radiation intensity depended on wavelength and temperature. Planck discovered a radiation law that matched those results beautifully. But the law required a strange assumption. He proposed that the tiny oscillators in the walls of the heated cavity could not have just any amount of energy. They could only possess energy in discrete levels. More importantly, when they exchanged energy with radiation, they did so in definite steps. Energy was not sliding smoothly up and down like water rising in a glass. It was being traded in small packets. The size of those packets depended on the frequency of the radiation. Higher frequency radiation came in larger energy packets. Lower frequency radiation came in smaller ones. This relationship introduced a new constant into physics, now called Planck's constant. It is an extremely tiny number, but its meaning is enormous. Planck's constant sets the scale of quantum behavior. It tells nature how large the smallest meaningful steps of energy exchange are for radiation of a given frequency. In ordinary life, Planck's constant is so small that these steps are hidden. Everyday energy exchanges feel smooth because the individual packets are far too tiny to notice. Pouring water from a jug looks continuous, even though the water is made of molecules. In a similar way, warming a room feels continuous, even though the deeper exchange of energy can involve discrete quantum steps. The smoothness of ordinary experience is real at human scales, but it is not the whole story. Planck's proposal solved the ultraviolet catastrophe because it changed how high-frequency radiation could receive energy. High-frequency radiation required larger energy packets. At normal temperatures, there was not enough available thermal energy to populate those high-frequency modes freely. The higher the frequency, the more costly each packet became. As a result, the impossible flood of ultraviolet radiation was cut off. The black-body curve rose, peaked, and fell just as experiments showed. This was the birth of the quantum. At first, it looked like a mathematical trick. Planck himself was cautious. He had not set out to say that nature was fundamentally grainy. He was trying to solve a stubborn problem with heated objects. Yet the solution carried a message that physics could not ignore. If the radiation law worked only when energy exchange came in discrete amounts, then perhaps energy was not always as continuous as classical theory had assumed. That idea was small at first, almost hidden inside the mathematics, but it had a habit of growing. It suggested that the deep rules of reality might not match the smooth appearance of the everyday world. A glowing object, something as simple as a heated cavity or a red-hot piece of metal, was quietly pointing toward a new kind of physics. Not because it behaved wildly, but because it behaved too precisely for the old theory to explain. The measurements were calm, the curve was smooth, the catastrophe belonged not to nature, but to the theory trying to describe it. This is one of the more beautiful patterns in science. A revolution does not always begin with a thunderclap. Sometimes it begins with a careful graph, a stubborn mismatch, and a scientist trying to make the numbers fit without quite realizing that the floor beneath physics has started to move. The innocent question was why hot things glow the way they do. The answer was that energy, at the smallest scales, may not flow in any amount whatsoever. It may arrive in portions. It may be exchanged in steps. Beneath the continuous warmth of a fire and the steady light of a star, nature may be counting. And once physics saw those tiny steps, the universe would never look quite continuous again. Light had already shown one strange habit. In the glow of hot matter, it seemed to trade energy in small packets rather than in one perfectly smooth flow. That idea had begun with Max Planck, almost cautiously, as a way to explain black-body radiation. It was a mathematical key that opened a locked door, though at first it was not obvious what kind of room lay on the other side. Then Albert Einstein pushed the door much wider. In 1905, Einstein published several extraordinary papers, the kind of year most scientists would be pleased to have spread across several lifetimes, rather than squeezed into 12 months. One of those papers looked at a puzzle called the photoelectric effect. The name sounds technical, but the basic observation is simple. When light shines on certain metal surfaces, electrons can be knocked out of the metal. Light arrives, electrons leave. It seems, at first, like a neat little exchange between radiation and matter. Classical wave theory had a natural way to imagine this. If light was a wave, then brighter light should carry more energy. A faint beam should be weak. A bright beam should be strong. So if a beam of light was too weak to knock electrons from the metal, increasing the brightness ought to help. Give the wave more intensity, let it push harder, and eventually the electron should receive enough energy to escape. That was the sensible expectation. It feels obvious in the same way that a bigger ocean wave should shove a floating object more forcefully than a smaller one. But the metal did not behave as expected. Experiments showed that brightness was not the only thing that mattered. The frequency of the light was crucial. Light below a certain frequency could fail to release electrons no matter how bright it became. A very intense beam of low-frequency light could shine on the metal, delivering plenty of total energy, and still not free the electrons in the expected way. Meanwhile, light above a certain frequency could release electrons even when it was faint. The electrons did not seem impressed by the total amount of light arriving over time. They seemed to care about the energy carried by each individual portion of light. This was deeply awkward for the classical wave picture. If light were only a smooth wave spreading its energy across space, then electrons in the metal might be expected to gradually absorb energy from the wave until they had enough to escape. With enough brightness, or enough time, low-frequency light should eventually do the job. But that delay was not observed in the way classical theory suggested. When the right frequency of light struck the metal, electrons were emitted almost immediately. When the frequency was too low, making the light brighter did not fix the problem. Einstein proposed a bold explanation. He took Planck's quantum idea more literally than Planck originally had. Perhaps light was not just exchanging energy with matter in discrete amounts during blackbody radiation. Perhaps light itself, in some circumstances, behaved as if it came in individual packets of energy. Those packets are now called photons. Einstein argued that each light packet carried an amount of energy linked to its frequency. Higher frequency light carried more energy per packet. Lower frequency light carried less. For an electron to escape from a metal, it had to receive enough energy in one encounter to overcome the hold of the metal surface. If a photon did not carry enough energy, the electron could not escape. Sending more low-energy photons made the light brighter, but each photon was still too weak to free an electron. It was like trying to buy something that cost £1 using a pile of halfpenny coins at a shop that, very unreasonably, only accepts single coins large enough to cover the full price. Nature can be oddly strict at the counter. If the photon had enough energy, however, the electron could be released. Any extra energy could appear as motion in the escaping electron. This explained why frequency set the threshold, while brightness affected how many electrons might be emitted once the frequency was high enough. Brighter light meant more photons arriving. More suitable photons meant more electrons could be knocked free. But brightness alone could not make each photon more energetic. The colour, or more precisely the frequency, mattered. This was the photoelectric effect, and it offered powerful support for the idea that light could behave like particles. Yet Einstein was not simply saying that light was only a stream of tiny pellets. That would have been too easy, and quantum physics does not often choose the easy hallway when there is a stranger one available with poor lighting and excellent experimental evidence. Light was already known to behave like a wave. It produced interference and diffraction. It spread, overlapped, and formed patterns that made perfect sense when light was treated as an electromagnetic wave, as described by James Clerk Maxwell. So the new picture was not a clean replacement of waves with particles. It was something more unsettling. Light could behave like a wave in some experiments and like a collection of particles in others. It could spread out and interfere, yet also arrive in discrete packets when interacting with matter. This became known as wave-particle duality, though even that phrase can make the situation sound neater than it really is. Light was not politely switching costumes backstage. It was revealing that the older categories of wave and particle were not deep enough to describe it fully. The photon idea was not accepted instantly. It had to fight its way through careful doubt, which is exactly what strong scientific ideas should do. Robert Millikan, an American physicist, carried out precise experiments on the photoelectric effect in the years that followed. His measurements confirmed Einstein's equation for the relationship between light frequency and electron energy. Yet Millikan himself was initially reluctant to accept Einstein's interpretation of a light quanta. This is a useful detail because it shows that quantum physics did not become accepted because everyone woke up one morning in a poetic mood and decided the universe should be weird. The evidence had to accumulate. The numbers had to behave. The experiments had to be repeated. Millikan's work helped confirm that Einstein's explanation was right, even if the idea seemed difficult to swallow. The photoelectric effect showed that Planck's quantum was not just a convenient trick for heated cavities. It had become a statement about light itself. Energy was not merely being calculated in packets to rescue a graph. Light could interact with matter as though those packets were physically meaningful. This changed the story. Planck had found that blackbody radiation made sense if energy exchange happened in discrete steps. Einstein showed that those steps were not confined to the walls of a glowing object. They belonged to the behavior of radiation itself. The quantum had moved from a mathematical solution into the physical world. It had become something that could knock electrons out of metal. That may sound like a small promotion, but it was enormous. It meant the smooth beam of light crossing a room was hiding a second nature. In one experiment, it could behave as a wave. In another, it could arrive as individual photons. The glow of a lamp, the shimmer of sunlight on glass, the invisible infrared warmth from a radiator, and the high-energy ultraviolet light that can release electrons from a surface were all part of the same deeper puzzle. Light which had once seemed so elegantly understood, had become stranger and richer. And the strangest part was not that science had become less reliable, it had become more reliable. The photon idea explained what classical physics could not. It matched experiment. It made predictions. It showed that the universe was not making things up as it went along, even if it sometimes appeared to have a very unusual writing style. A beam of light could still fill a room softly. It could still warm the skin, brighten a page, or fade the edge of a curtain over many years. But beneath that familiar gentleness was a sharper truth. Light could arrive in pieces. Each photon carried its own small allowance of energy, set by its frequency, and matter responded to those packets with extraordinary precision. The quantum had stepped out of the furnace glow and into the beam itself. By the time light had begun behaving like both a wave and a stream of photons, another mystery was waiting quietly inside the matter that light touched. The atom had become impossible to ignore. For centuries, the idea of atoms had drifted between philosophy and science. Ancient thinkers had imagined matter divided into tiny indivisible pieces, but imagining something and measuring it are very different things. By the early 20th century, atoms had become far more than a clever guess. Chemistry made sense only if elements were built from repeatable units. Gases behaved in ways that suggested countless small particles moving and colliding. Brownian motion, the jittery movement of tiny particles suspended in liquid, gave strong evidence for the restless motion of molecules. Matter clearly behaved as though it were made of tiny structured pieces, but what those pieces were like inside was still deeply unclear. This was not a small detail. The whole visible world depended on atoms being stable. Wood stayed wood. Iron stayed iron. Water remained water unless something changed its chemistry. A stone did not suddenly dissolve into light because its atoms got bored in the afternoon. Matter had structure, persistence, and reliable behavior. Yet the inner architecture of the atom was still a puzzle, and classical physics was about to make that puzzle much worse. In the early 1900s, one of the most important clues came from Ernest Rutherford and the gold foil experiment. Rutherford had already worked extensively on radioactivity, and at the University of Manchester, his collaborators Hans Geiger and Ernest Marsden carried out a beautifully simple and revealing experiment. They fired alpha particles at extremely thin gold foil and watched how the particles scattered. At the time, one influential picture of the atom was J.J. Thomson's plum pudding model. Thomson had discovered the electron in 1897, showing that atoms contained negatively charged particles. In his model, the atom was imagined as a spread-out positive charge with little negative electrons embedded inside it, rather like raisins in a pudding. It was not a bad guess for the moment. It gave the atom internal structure, and it did not yet require anything too alarming. The gold foil experiment changed that. Most alpha particles passed straight through the foil, as if the gold atoms were mostly empty space. Some were deflected slightly. But a very small number bounced back at large angles, as though they had struck something tiny, dense, and strongly positive. Rutherford later described the surprise by comparing it to firing a shell at tissue paper and having it come back. That image has survived because it captures the shock rather well. The atom, which had seemed like it might be a soft, spread-out object, had revealed a hard, central concentration. Rutherford proposed the nuclear model of the atom. In this picture, nearly all of an atom's mass and positive charge were concentrated in a small central nucleus. The negatively charged electrons occupied the much larger space around it. The scale was astonishing. If the nucleus were enlarged to the size of a small pebble, the outer region of the atom would stretch across something like a stadium. The exact comparison depends on the atom and the model being used, but the point is clear enough. Matter feels solid, but atoms are mostly empty space, with their mass concentrated in a tiny central core. This was a brilliant breakthrough. It was also a disaster. The problem was the electrons. In Rutherford's model, electrons seemed to move around the positive nucleus somewhat like planets around the Sun. The comparison was tempting, but it could not work under classical electromagnetic theory. According to Maxwell's theory, an accelerating electric charge should emit electromagnetic radiation. An electron moving in a curved path around a nucleus is constantly accelerating because its direction is constantly changing, so it should radiate energy. As it lost energy, it should spiral inward. Very quickly, it should crash into the nucleus. Classical physics seemed to predict that atoms should collapse. This was more than inconvenient. It was a direct threat to the existence of stable matter. If classical theory were applied straightforwardly, atoms should not sit calmly as the building blocks of tables, air, skin, stars, teacups, and biscuits. They should rapidly destroy themselves. The universe should not have the chemistry required for rocks, oceans, lungs, or late-night snacks. This is one of those moments where being wrong is actually fortunate. A universe made according to that prediction would have been over before anyone could complain about it. But atoms did not collapse. Matter remained stable, and atoms also had another remarkable habit. They interacted with light in extremely specific ways. When the light from hot gases was passed through a prism or a spectroscope, it did not always appear as a smooth rainbow. Instead, individual elements produced sharp-coloured lines at particular wavelengths. Hydrogen had its own pattern. Sodium had its famous yellow lines. Neon, mercury, helium, and other elements each produced their own characteristic set. These spectral lines were like coloured fingerprints. They revealed that atoms did not emit and absorb light in just any amount or at just any colour. They selected particular wavelengths with astonishing precision. This mattered enormously. Spectral lines allowed scientists to identify elements on Earth and in distant stars. The element helium was first detected in the spectrum of sunlight before it was found on Earth, which is a rather elegant way for an element to introduce itself. Light from distant objects could be split into its colours, and hidden in those lines was information about chemical composition, motion, temperature, and physical conditions. The universe was sending coded messages through light, and spectroscopy became one of the ways to read them. But why did atoms have those particular fingerprints? Classical physics had no satisfying answer. If electrons could orbit at any distance and hold any energy, then atoms ought to emit a broad spread of light as electrons change their motion. Instead, atoms emitted and absorbed light at precise energies. Once again, nature was refusing to behave continuously. In 1913, Niels Bohr proposed a daring model of the hydrogen atom. He kept Rutherford's central nucleus, but changed the rules for the electron. Bohr suggested that the electron could occupy only certain allowed orbits around the nucleus. While it remained in one of those allowed orbits, it did not radiate energy and spiral inward. It was stable. The electron could move between allowed orbits, but it could not settle halfway between them. When it jumped from a higher energy orbit to a lower one, the atom emitted a photon. When it absorbed a photon with the right energy, the electron could jump upward. This was the idea of quantum jumps. The energy of the emitted or absorbed photon was tied to the difference between the electron's allowed energy states. In spoken form, the relationship is simple enough. The energy of the photon equals Planck's constant multiplied by the frequency of the light. That meant each spectral line corresponded to a specific energy difference inside the atom. Hydrogen did not produce its coloured lines randomly. Its spectrum was a visible record of its internal quantum structure. Bohr's model worked especially well for hydrogen, the simplest atom, with one electron around one proton. It explained the pattern of hydrogen's spectral lines with impressive accuracy. It also gave a reason why atoms could be stable. Electrons were not free to spiral down through every possible energy. They were restricted to certain allowed states. This was not the final picture of the atom. Later quantum mechanics would replace Bohr's neat circular orbits with orbitals, wave functions, and probability distributions. Electrons would stop looking like tiny planets entirely, but Bohr's model was a crucial bridge. It took the quantum idea from light and heat and placed it inside the structure of matter itself. That step was profound. The atom was no longer just a miniature object obeying smaller versions of familiar rules. It was governed by new rules. Its electrons could not have any energy they pleased. Its light came from transitions between allowed states. Its colours were not decorative accidents, but precise signals from within. A glowing gas tube, a star's spectrum, or the faint light from hydrogen in space was revealing the hidden architecture of matter. The connection to photons was now unavoidable. Light arrived in packets, as Einstein had argued. Atoms emitted those packets when their electrons changed energy states. The colour of each photon depended on the size of the quantum jump that produced it. A spectral line was not merely a stripe of colour. It was the trace of an atom changing its internal state by a definite amount. So the story that began with heated objects had reached the heart of matter. First, energy seemed to come in packets. Then light itself behaved as if it arrived in photons. Now atoms were showing that their internal energies were restricted too. The universe was not continuous all the way down. Beneath the smoothness of everyday matter, there were allowed states, forbidden gaps, and precise transitions. The atom had become stable not by obeying classical intuition, but by disobeying it in exactly the right way. By now, light had become wonderfully difficult to pin down. It could spread like a wave, interfere like a wave, and pass through space as an electromagnetic ripple. Yet in the photoelectric effect, it behaved as if it arrived in individual photons, each carrying a definite packet of energy. Light had not stopped being wave-like, but it had also refused to be only a wave. Then physics asked a dangerous question. What if matter could do the same thing? At first, that sounds almost unreasonable. Matter feels solid. It has weight, shape, location, and stubbornness. A stone does not flow through a doorway as a gentle wave of possibility. A chair does not diffract around a table leg, although that would make moving furniture slightly more graceful and considerably more alarming. Matter seems to belong to the world of things, while waves seem to belong to the world of motion, ripples, sound, light and water. But quantum physics had already begun to blur that tidy separation. If light, which had been understood as a wave, could behave like particles, perhaps particles could also have wave-like properties. This was the bold proposal made by Louis de Broglie in the early 1920s. De Broglie suggested that electrons and matter more generally could be associated with wavelengths. The wave-particle puzzle was not just a strange feature of light. It might be woven into matter itself. This idea became known as matter waves. In plain language, de Broglie proposed that every moving object has a wavelength connected to its motion. The faster and more massive the object is, the shorter that wavelength becomes. The lighter and more microscopic the object is, the more noticeable its wave behaviour can become. This is why electrons can reveal wave-like effects, while footballs, pebbles, people, and sleepy cats do not usually form delicate interference patterns as they cross a room. The equation behind this idea can be expressed simply. The wavelength of a moving object equals Planck's constant divided by its momentum. The important part is Planck's constant. It is extremely small, which means that for ordinary objects the wavelength is unbelievably tiny. A walking person has a matter wavelength so small compared with a person's size that it is not useful in everyday experience. It is not merely too small to see with the naked eye. It is vastly smaller than atoms, smaller than the scales where ordinary measurement could make it relevant. So the person behaves, for all practical purposes, like a classical object with a fairly definite position and motion. A person walking down a hallway does not need to be treated like a ripple, which is good news for hallways everywhere. For an electron, however, the situation is different. An electron has a very small mass. Its wavelength can be comparable to atomic distances under the right conditions. That means its wave-like nature can show up in experiments. It is not hidden beneath the huge scale of everyday matter. It becomes part of how the electron behaves. This was not just a poetic suggestion. It was tested. One of the key confirmations came from the Davison-Germer experiment in 1927. Clinton Davison and Lester Germer were studying how electrons scattered from a crystal of nickel. A crystal is not just a lump of material. Its atoms are arranged in a regular repeating pattern, with tiny spacings between layers. That makes crystal a natural kind of measuring structure for waves with extremely short wavelengths. When waves encounter a regular array like this, they can diffract and interfere, producing stronger signals in some directions and weaker signals in others. This kind of behavior was already known from waves. X-rays, which have very short wavelengths, could diffract from crystals because their wavelengths were similar to the spacing between atoms. The startling discovery was that electrons could do something similar. Davison and Germer observed electron scattering patterns that matched the predictions of de Broglie's matter waves. Electrons were not simply bouncing off the crystal like tiny classical pellets. They were producing diffraction patterns, as waves do. This was a quiet but enormous collapse of common sense. The electron, which had been discovered by J.J. Thomson as a particle-like carrier of negative electric charge, now had to be understood as something with wave-like behavior too. It could hit a detector as a localized event, but its motion through an experiment could be described by a wave. It was not a little planet. It was not a tiny bead. It was not a miniature speck following a perfectly definite path in the old familiar way. It was a quantum object. Matter waves also helped make sense of one of the strangest features of Niels Bohr's atomic model. Bohr had proposed that electrons in hydrogen could occupy only certain allowed orbits. The model worked surprisingly well for hydrogen spectral lines, but the allowed orbits could seem arbitrary. Why those orbits, and not others? Why should an electron be permitted to exist at one energy, but not at a slightly different one? De Broglie's idea offered a more natural picture. If the electron had wave-like properties, then a stable electron state around the nucleus could be imagined as a standing wave. A standing wave is a wave pattern that fits neatly into a confined space, reinforcing itself rather than cancelling itself out. A vibrating guitar string produces only certain stable patterns, because the wave must fit the length of the string. If the pattern does not fit, it cannot remain as a steady vibration. Something similar could be imagined for the electron in an atom. Only certain wave patterns could fit around the nucleus in a stable way. Those stable patterns corresponded to allowed states. Other would-be patterns would fail to join smoothly with themselves, so they would not represent stable electron states. Bohr's allowed orbits no longer seem like rules simply pasted onto the atom. They began to look like a sign that electrons were wave-like objects constrained by the geometry of the atom. This was still not the final modern picture. Electrons do not truly move around the nucleus as neat little waves drawn on circular tracks. Later quantum mechanics would describe them through wave functions and orbitals, giving probability distributions rather than miniature solar systems. But de Broglie's idea was a vital step toward that deeper understanding. It showed why the old image of electrons as tiny planets circling a tiny sun could not survive. The planetary atom had always been tempting because it felt familiar. A central nucleus, orbiting electrons, little paths, little speeds, little worlds. It was simple to imagine. But atoms are not tiny clockwork models of the solar system. The electron is not a speck with a hidden road painted around the nucleus. Its behavior is shaped by wavelength, probability, allowed states, and interference. This does not mean that matter is unreal or that solidity is an illusion in a careless sense. A table is still a table. A wall is still best treated as a wall, not as an optional suggestion. Everyday matter is stable and reliable because quantum rules work with extraordinary consistency. But the reason matter has structure is not the same as the reason a planet has an orbit. At the atomic scale, the rules are different. That is the strange elegance of matter waves. They do not make the world less real. They make it more subtle. They reveal that the familiar solidity of matter rises from hidden patterns that ordinary intuition was never built to picture. A beam of light could arrive in pieces. An electron could spread like a wave. And the atom, once imagined as a tiny mechanical system, began to look like something far stranger and more delicate, a place where matter itself had to fit into the allowed shapes of quantum possibility. The wave-like nature of matter is not just a clever idea written on paper. It shows up in one of the most famous experiments in all of physics, an experiment so simple in outline that it almost feels suspicious. There is a source, a barrier with two narrow openings and a screen behind it. That is the basic arrangement. Not a thunder machine, not a cosmic portal, not a laboratory apparatus that looks as if it should be guarded by a nervous assistant with goggles. Just two slits and a place for the results to appear. Yet from that simple arrangement comes one of the clearest signs that the quantum world does not behave like the everyday world. The easiest way to begin is with ordinary waves. Imagine water waves moving across the surface of a pond toward a wall with two narrow gaps in it. When the wave reaches the wall, part of it passes through one gap and part through the other. On the far side, two new sets of ripples spread outward. Where the crests of the waves meet other crests, they reinforce each other and make a stronger wave. Where a crest meets a trough, they cancel partly or completely. This creates an interference pattern, a regular arrangement of stronger and weaker regions. Light can do something similar. In the early 19th century, Thomas Young performed his famous double-slit experiment with light and showed that it could produce an interference pattern. This was powerful evidence that light behaved as a wave. If light were only a stream of tiny classical particles, one might expect it to pass through the two slits and form two bright bands on the screen, one behind each opening. Instead, Young observed alternating bright and dark bands, the signature of wave interference. Light seemed to spread through both openings, overlap with itself, and form a pattern that only made sense if wave behavior was real. For a while, this helped secure the wave theory of light. Then quantum physics arrived and made the whole situation more interesting, because light was later shown to arrive in photons, and electrons were shown to have matter waves. The double-slit experiment became more than an elegant demonstration from older optics. It became a doorway into the shape of quantum possibility. The truly strange version begins when particles such as selectrons are sent toward two slits. If electrons were simply tiny classical pellets, the expectation would be straightforward. Some electrons would pass through the left slit, some would pass through the right slit. Over time, they would build up two main piles on the screen, matching the two openings. It would be like firing tiny grains of sand through two gaps in a fence. The grains might scatter a little, but the result would still be two broad clusters. That is not what happens when the experiment is arranged so that the electron's wave-like behavior can appear. Instead, over many electrons, an interference pattern gradually builds on the screen. At first, each electron lands as a single localized mark. One dot here, another dot there, then another somewhere else. Each detection looks particle-like. But as more and more electrons arrive, the dots do not form just two simple bands. They arrange themselves into a pattern of alternating high and low probability, just like wave interference. The electron arrives one at a time, but the final distribution looks as though a wave has passed through both slits and interfered. This is the quiet shock of the double slit experiment. The electron is detected as a single event, but the pattern of many detections reveals wave-like behavior. It is not just that a crowd of electrons somehow pushes and jostles itself into a wave pattern, because the experiment can be done with electrons sent one at a time. There need not be a crowd travelling together. Each electron is prepared, sent through, and eventually detected. Only after many repetitions does the hidden pattern become clear. The same basic lesson has been shown not only with electrons but also with photons, atoms, and even large molecules under carefully controlled conditions. The larger and more complex the object becomes, the harder it is to preserve the delicate quantum behavior, because interactions with the environment tend to destroy visible interference. Still, the principle is clear. The wave-like behavior of matter is not a metaphor. It appears in real experimental patterns. This is where a careful explanation matters, because the double slit experiment is often described in ways that make it sound as if particles are shy, dramatic, or emotionally affected by being watched. They are not tiny performers getting stage fright. The experiment does not show that electrons have thoughts, intentions, or a secret fondness for privacy. Measurement in quantum physics means a physical interaction that makes certain information available. If an apparatus is arranged to determine which slit the electron goes through, that interaction changes the conditions of the experiment. When which path information is available, the interference pattern disappears. The result becomes more particle-like. When that path information is not available, the interference pattern can appear. The key is not human consciousness staring intensely at the apparatus. The key is whether the physical setup preserves or destroys the conditions required for interference. A detector, a scattered photon, or an interaction with the environment can be enough to change what happens. The universe is not waiting for a person in a lab coat to squint at it. Which is good, because the universe has had a very long time to behave before lab coats were invented. What quantum physics predicts is not always a definite path in the familiar classical sense. Instead, it predicts a probability pattern. It can say, with extraordinary accuracy, where particles are more likely or less likely to be detected after many repetitions of the same experiment. It does not necessarily describe each electron as having travelled through one definite slit in the ordinary way before measurement. That is the difficult part. The mathematics gives a distribution of possible outcomes, and the experiment confirms that distribution with remarkable precision. This does not mean quantum physics is vague. It is almost the opposite. The single event may be unpredictable in detail, but the pattern formed by many events is highly predictable. One electron lands somewhere. Many electrons reveal the shape of the underlying probabilities. The randomness is not carelessness. It is structured randomness, if that phrase is allowed to sit quietly without causing trouble. The double slit experiment gathers many earlier ideas into one simple image. Planck's quantum show that energy could be exchanged in packets. Einstein's photons showed that light could arrive in pieces. De Broglie's matter wave suggested that electrons could have wavelengths. The double slit experiment shows what that means in practice. An electron can be detected as a particle-like dot, while its behavior across the whole experiment reflects wave-like probability. This is why the experiment has such lasting power. It does not merely tell us that the microscopic world is strange, it shows the strangeness in a pattern that can be built up dot by dot, patiently, almost gently, on a screen. The shape appears slowly, not as a dramatic announcement, but as evidence accumulating one small mark at a time. An electron is not simply a tiny planet, a tiny bead, or a tiny grain of sand. It is a quantum object, and its possibilities can interfere. The double-slit experiment lets those possibilities leave a visible trace. In the end, the screen does not show only where particles landed. It shows the strange hidden geometry of what nature allowed before they arrived. The double-slit experiment leaves behind a pattern that seems almost too delicate to belong to the physical world. One electron lands as a single mark. Many electrons, arriving one by one, slowly build an interference pattern. The result looks as though something wave-like has passed through both openings, even though each final detection appears as one definite event. To describe this kind of behavior properly, physics needed more than pictures. It needed a new language. That language arrived in the work of Erwin Schrödinger. In the mid-1920s, Schrödinger developed a wave equation that became one of the central foundations of quantum mechanics. The equation described how the quantum state of a system changes over time. It did not simply say that particles were tiny waves in the ordinary sense. It gave physicists a mathematical way to calculate how quantum possibilities spread, evolve, overlap, and eventually produce measurable outcomes. The important idea is not the algebra itself. For a calm evening, algebra can remain politely outside with its coat on. The essential point is that Schrödinger's equation allowed scientists to track the behavior of something called the wave function. The wave function is one of the most important ideas in quantum physics, and also one of the easiest to misunderstand. It is not simply a physical wave like a ripple moving across a pond. A water wave is a movement of water. A sound wave is a pattern of pressure moving through air or another material. A light wave, in classical physics, is an oscillation of electric and magnetic fields. The wave function is more abstract than these. It is a mathematical description of a quantum system. That may sound less satisfying than imagining a tiny visible ripple, but it is far more powerful. The wave function contains information about the possible outcomes of measurements. For an electron, it can describe where the electron may be found, what momentum it may have, or how its quantum state changes under particular conditions. It is not a little cloud of matter smeared through space in quite the same way that mist is spread through air. It is a tool for describing the structure of possibility. At first, there was debate about what Schrödinger's wave really meant. Schrödinger himself hoped for a fairly physical interpretation, but Max Born made the crucial step that shaped modern quantum mechanics. Born argued that the wave function should be understood in terms of probability. More precisely, it could be used to calculate the likelihood of finding a particle in a particular place, or obtaining a particular result when a measurement is made. This changed the meaning of the wave. The wave function did not tell physicists that the electron was simply spread out as an ordinary substance. It told them how probabilities were distributed. Where the wave function gave a stronger probability, the particle was more likely to be detected. Where it gave a weaker probability, detection was less likely. In experiments repeated many times, those probabilities became visible as patterns. This is exactly what makes the double-slit experiment so powerful. The interference pattern is not formed, because each electron splits into a little classical fragment and travels like dust through both slits. Nor is it formed because the electron secretly behaves like a tiny marble, with a definite hidden path that classical physics simply failed to notice. In the quantum description, the wave function evolved through the experimental arrangement. The possible paths contribute to the final probability pattern. Where possibilities reinforce, detections become more likely. Where possibilities cancel, detections become rare. Then, when an electron is detected, it appears at one definite location. That mixture can feel unsettling. Quantum mechanics often predicts probabilities rather than single guaranteed outcomes. But this does not make it vague, mystical, or casually hand-wavy. In fact, quantum mechanics is one of the most precise scientific theories ever created. Its predictions have been tested in atomic physics, particle physics, chemistry, electronics, optics, and many other fields with extraordinary success. The theory may describe probabilities, but it does so with remarkable accuracy. It is not shrugging at reality. It is counting possibilities with terrifying discipline, which is perhaps the most mathematical kind of calm. Schrödinger's work also changed the picture of the atom. Earlier, Niels Bohr had imagined electrons occupying certain allowed orbits around the nucleus. That model worked impressively well for hydrogen, but it still carried the flavour of a tiny solar system. The electron seemed to move along a path, circling the nucleus like a little planet. Useful as that picture was, it was not the deeper truth. With wave mechanics, the idea of fixed electron orbits began to give way to orbitals. An orbital is not a small track around the nucleus. It is a region described by the wave function, showing where an electron is likely to be found around an atom. Different orbitals have different shapes and energy levels. Some are roughly spherical. Others have more complex forms, with lobes and patterns that reflect the mathematics of the electron's quantum state. These orbitals help explain the structure of atoms and, eventually, the behavior of chemistry. The way electrons occupy orbitals shapes how atoms bond, how molecules form, and why different elements have different properties. The familiar world of materials, colours, reactions, crystals, metals, and living chemistry rests on this quiet mathematical foundation. The old image of electrons as little planets was charming, but the universe had chosen something more subtle. The wave function also explains why quantum physics can feel so different from ordinary experience. In daily life, objects usually appear to have definite locations and paths. A falling mug does not seem to explore a carefully arranged landscape of possibilities before selecting the floor. It simply falls, usually with a regrettable amount of confidence. But at microscopic scales, the wave function is not optional. It is the central description. It tells physicists how the quantum state evolves before measurement, and how likely different results are when measurement occurs. This is why Schrödinger's equation matters so deeply. It gave quantum physics a structure. It made the strange behaviour of electrons, photons, and atoms calculable. It connected the wave-like patterns seen in experiments to a mathematical rule that could be used again and again. Quantum possibility was no longer just a surprising pattern on a screen. It had become something physics could describe with precision, and perhaps that is the most important point. Quantum physics is strange, but it is not chaos. It does not say that anything can happen for no reason. It says that at the smallest scales, nature follows rules that do not look like the rules of everyday objects. The rules involve wave functions, probabilities, allowed states, and measurable outcomes. They can feel unfamiliar because human intuition was shaped by stones, rivers, bodies, tools, and weather, not by electrons moving through slits. The wave function is the quiet centre of that unfamiliar world. It does not turn quantum physics into an easy picture, but it gives the mystery a form. It shows how possibility changes with time, how interference patterns arise, and why the atom is not a miniature clockwork machine. The electron is not simply here or there in the old classical sense before every measurement. It is described by a wave function, and from that wave function comes the pattern of what may be found. In the double slit experiment, that pattern becomes visible dot by dot. In the atom, it becomes the shape of orbitals. Across physics, it becomes one of the deepest ways science has found to describe reality before it settles into an observed result. The wave function gives quantum physics a way to describe possibility with extraordinary precision. It shows how the state of a particle can spread, evolve, interfere, and produce probabilities for what may be found when a measurement is made. But once particles are described in this wave-like way, another idea appears almost naturally. It is one of the most famous principles in all of physics, and one of the most commonly misunderstood. This is the uncertainty principle. Werner Heisenberg introduced it in the late 1920s, at a time when quantum mechanics was still being assembled into its modern form. The name can make it sound like a statement about confusion, or bad equipment, or scientists staring sadly at blurry instruments while muttering into their notebooks. But that is not what Heisenberg meant. The uncertainty principle is not simply a complaint that measurements are difficult. It is a limit built into the structure of quantum systems themselves. The most familiar version concerns position and momentum. Position means where something is. Momentum means how much motion it has, taking account of both its mass and its velocity. In everyday life, these two things seem perfectly able to coexist. A tennis ball can have a location and a speed. A car can be here, moving that way, at that pace. A drifting leaf can be tracked as it turns through the air. If the measurement is poor, that is usually a practical problem. Better cameras, better timing, and better instruments should improve the answer. At the quantum scale, something deeper is going on. For a particle such as an electron, quantum physics says that position and momentum cannot both be assigned perfectly exact values at the same time. The more precisely the position is defined, the less precisely the momentum can be defined. The more precisely the momentum is known, the less sharply the position can be pinned down. This is not because the electron is hiding information in a tiny coat pocket. It is because the quantum state itself does not contain those two perfectly definite properties together in the way classical physics would expect. The relationship is often written mathematically, but its meaning can be spoken clearly. The uncertainty in position multiplied by the uncertainty in momentum can never be smaller than Planck's constant divided by 4 pi. The exact expression matters in formal physics, but the essential message is simpler. There is a lower limit to how much these uncertainties can be reduced together. One can squeeze one side of the description, but the other side spreads out in response. Nature does not allow both to shrink to zero at once. Wave behavior makes this less mysterious. Imagine a wave that stretches smoothly across a long distance, with a very regular wavelength. Because the wavelength is well defined, its momentum is also well defined in the quantum description. But such a wave is spread out. It does not have one sharply defined location. It belongs to a broad region. Now imagine trying to make the wave into a tight packet, concentrated in a small space. To do that, many different wavelengths have to be combined. The packet becomes more localized, but because it contains a mixture of wavelengths, its momentum becomes less definite. This is not a flaw in the measuring device. It is a feature of waves. A perfectly pure tone continues smoothly and regularly, but it is spread over time. A very short click is sharply located in time, but it contains many frequencies. The same kind of trade-off appears in quantum physics. A sharply localized particle requires a wave function made from a range of momenta. A particle with a very definite momentum is described by a wave function spread over a wider region of space. So uncertainty is not ignorance in the ordinary sense. It is not that the electron secretly has an exact position and exact momentum, while scientists are merely too clumsy to uncover them. In standard quantum mechanics, the combined exactness simply is not there before measurement in the classical way. The electron is not a tiny pellet following a perfectly definite path that is hidden only because the laboratory lights are not bright enough. It is a quantum object described by a wave function, and that description has built-in limits. This point matters because the uncertainty principle is sometimes used loosely, as if it means everything is unknowable, reality is vague, or facts have gone on holiday. None of that follows. Quantum mechanics is not a theory of helpless confusion. It gives extremely accurate predictions. It says very clearly which combinations of quantities can be known precisely together and which cannot. The uncertainty principle does not remove order from nature. It reveals a different kind of order. It also helps explain why atoms are stable. In the older classical picture, an electron orbiting a nucleus should lose energy and spiral inward. But if an electron were squeezed down into the nucleus, its position would become extremely well defined. According to the uncertainty principle, that would make its momentum highly uncertain and, in practical terms, would involve a very large spread in possible motion. Confining an electron into a tiny region costs energy. This helps prevent the electron from simply collapsing into the nucleus. Atomic stability also depends on other quantum principles, including the structure of allowed energy states, and for many electron atoms the Pauli exclusion principle. But uncertainty is part of the deeper reason matter does not behave like a miniature classical catastrophe. This is another place where the quantum world quietly protects the ordinary one. The solidity of a table, the shape of a molecule, the persistence of an atom, and the chemistry inside living cells all depend on rules that are completely unlike the rules of little planets circling little suns. Matter remains stable, not because electrons are tiny beads held in neat mechanical tracks, but because quantum states have structure. The wave function spreads, allowed states form. Uncertainty limits how sharply certain properties can be fixed together. The uncertainty principle is unsettling because it changes what can be meant by a complete description. Classical physics imagined that a particle could, in principle, have an exact position and exact motion at every moment. Quantum mechanics does not simply make that picture harder to measure, it replaces the picture. The particle is described by a quantum state, and that state does not always translate into the crisp classical properties intuition expects. And yet, there is something quietly elegant about it. The uncertainty principle is not chaos disguised as profundity. It is a precise boundary. It tells us that nature is not infinitely sharp in every direction at once. At the smallest scales, reality has a kind of texture, a relationship between spread and motion, between where a quantum object may be found and how its movement may be described. The wave function was already a language of possibility. Heisenberg showed that this language comes with limits written into its grammar. Electrons are not simply little pellets with poorly measured paths. They are quantum systems whose properties arise from wave-like probability patterns. And once that is understood, uncertainty stops being a failure of knowledge and becomes something far stranger and far more important. One of the rules that allows atoms, matter, and the familiar world to exist at all. Uncertainty already shows that quantum systems do not always carry the neat, finished properties that everyday objects seem to possess. An electron is not simply a tiny pellet with a perfectly exact location and a perfectly exact momentum waiting to be uncovered. Its state has a structure, and that structure places limits on what can be sharply defined at the same time. Superposition takes that strangeness one step further. The word sounds rather grand, but the central idea can be stated calmly. In quantum physics, a system can be described as a combination of possible states before a definite outcome is obtained through measurement. It is not merely that scientists do not know which state the system is in. It is that the quantum description itself can involve multiple possibilities woven together in a precise way. This is where quantum physics is often dragged into nonsense. Superposition does not mean that every large object is literally doing every ordinary thing at once in the everyday sense. It does not mean a chair is both in the kitchen and on the moon because nobody has checked carefully enough. It does not mean the universe has abandoned all standards and is now improvising with jazz hands. Superposition is not a license to say anything mysterious and hope the word quantum makes it sound expensive. It is a specific mathematical principle, and it has been tested again and again. A careful example is electron spin. Spin is an intrinsic quantum property of particles. It behaves in some ways like angular momentum, but it should not be imagined too literally as a tiny sphere rotating on its axis. An electron is not a little planet spinning in space with a painted arrow on it. Still, spin can be measured along different directions, and the results are quantized. That means measurements give certain discrete outcomes, not a smooth range of all possible values. Before a measurement along a chosen direction, the electron spin state can be a superposition of the possible results for that measurement. When the measurement is made, one definite result is obtained. The important point is that this superposition is not a vague fog of ignorance. It is a precisely defined quantum state that can be used to calculate the probabilities of different outcomes. Photon polarization gives another useful example. A photon of light can have a polarization state, which describes the orientation of its electromagnetic vibration. A photon can be prepared in a polarization state that is a combination of possible outcomes for a different measuring arrangement. Pass that photon through a polarizing filter, and the result follows quantum probability rules. Rotate the filter, change the setup, and the probabilities change in a precise and predictable way. Atomic energy states offer another example. An atom can be placed in a superposition of energy states under carefully controlled conditions. When measured, a definite energy may be found, but before that measurement the quantum state may involve a combination of allowed energies. This is not the same as saying the atom is confused. The atom is not sitting there with a tiny clipboard, uncertain which box to tick. The superposition is the proper quantum description of its state. Paul Dirac helped give these ideas their elegant formal shape. In the development of quantum mechanics, Dirac created a powerful mathematical language for describing quantum states, observables, and combinations of states. His work helped show that superposition was not an optional curiosity pasted onto quantum theory. It was central to the structure of the theory itself. Quantum states could be added together in well-defined ways, and those combinations could produce measurable consequences. That last phrase matters. Superposition is experimentally testable. It is not just a philosophical mood. When quantum states combine, they can interfere. This interference can change the probabilities of outcomes, just as wave-like possibilities shape the pattern in the double-slit experiment. If superposition were only a fancy name for ignorance, quantum interference would not appear in the same way. The behavior of electrons, photons, atoms, and other quantum systems shows that the combined state has real predictive power. A famous early experiment connected to these ideas is the Stern-Gerlach experiment, carried out by Otto Stern and Walter Gerlach in the early 1920s. They sent a beam of silver atoms through a non-uniform magnetic field. If the atom's angular momentum behaved according to ordinary classical expectations, the beam might have spread into a continuous smear, because many orientations should have been possible. Instead, the beam split into distinct parts. This showed that angular momentum in the quantum world was quantized. Measurements produced discrete outcomes rather than a continuous range. Later understanding connected this kind of behavior to spin and the structure of quantum measurement. The experiment remains important because it gives a vivid example of something deeply quantum. A measurement does not always reveal a property drawn from a smooth menu of classical possibilities. It can produce one of a limited set of allowed results. Superposition fits naturally into that picture. A quantum system can be prepared in a state that is not simply one definite measurement outcome or the other. It may be a combination of outcomes relative to a particular measurement. Then, when the measurement happens, the result is one of the allowed values, with probabilities determined by the quantum state. This can feel slippery because everyday experience trains the mind to expect hidden definiteness. A coin under a cup is either heads or tails even before anyone looks. A letter in an envelope has definite words written inside. A book on a shelf has a definite position, even in a dark room. Not knowing is usually just not knowing. The fact exists, and the observer lacks access to it. Quantum systems do not always work that way, at least not in the simple classical sense. Before measurement, the state may not contain one pre-existing outcome waiting patiently to be revealed. The system may be in a superposition, and the measurement context helps determine which kind of definite outcome can appear. This does not mean reality is lawless. It means the old picture of properties as always fully settled in advance is not adequate. This connects directly to uncertainty. The uncertainty principle showed that certain pairs of properties, such as position and momentum, cannot both be assigned perfectly exact values at the same time. Superposition shows another side of the same deeper lesson. Quantum objects are not merely small versions of familiar objects. Their properties are described by states that can combine, spread, interfere, and yield discrete results only when measured in particular ways. The danger is to make this sound more mystical than it is. Superposition is strange, but it is not magical. It is mathematical, practical, and experimentally grounded. It helps explain interference, polarization, atomic transitions, quantum computing, and many of the technologies and measurements that depend on quantum control. It belongs not to fantasy, but to the most successful physical theory ever built. The ordinary world feels definite because large objects interact constantly with their surroundings. Their quantum possibilities become entangled with the environment so quickly that delicate superpositions are usually impossible to observe directly at human scales. A dust grain in sunlight, a warm cup, or a person walking across a room is being nudged, scattered from, warmed, cooled, and measured by the environment in countless ways. The world is not waiting in theatrical suspense for someone to glance over, but in carefully isolated quantum systems, superposition is real enough to shape what happens. A photon can be prepared in a combined polarization state, an atom can occupy a combination of energy states, an electron spin can be described as a superposition relative to a chosen measurement direction. These are not failures of description. They are the description. So superposition without the nonsense is this. Before measurement, a quantum system can be in a precise combination of possible states, and that combination determines the probabilities of the outcomes that may later be observed. It is one of the quiet engines of quantum physics, less like a magic trick and more like a rule book written in a language everyday intuition never had to learn. The world above the surface looks settled. The quantum world beneath it is not always settled in the same way. And from that difference comes much of the strangeness, power, and precision of modern physics. Superposition leads to one of the most awkward questions in physics. A quantum system can be described as a combination of possible states. Its wave function can evolve smoothly, spreading and changing according to precise mathematical rules. It can give probabilities for different measurement outcomes with astonishing accuracy. Then a measurement happens, and the world does not usually present a soft blur of possibilities. It presents one result. An electron is found here, not everywhere. A photon passes through this polarizing filter, or it does not. An atom emits a photon of a particular energy. A detector clicks in one place. The strange richness of quantum possibility seems to settle into a definite event. That is the measurement problem. It is not a small loose thread at the edge of quantum theory. It is one of its deepest unresolved conceptual puzzles. The mathematics of quantum mechanics tells us how a wave function changes over time, and it does this extremely well. But when a measurement is made, the theory appears to shift from a smooth evolution of possibilities to one definite outcome. Why that happens, what exactly counts as a measurement, and what this says about reality, are questions that still do not have one universally accepted answer. The traditional language for this is wave function collapse. Before measurement, the wave function may describe several possible outcomes. After measurement, only one outcome is observed. Collapse is the name often given to that apparent transition from a spread of possibilities to a single result. The word is dramatic, as if the wave function has fainted onto a sofa, but the idea is simple enough. The quantum description seems to reduce to the particular outcome that is actually found. The difficulty is understanding what collapse really means. Is it a physical process that actually happens in the world? Is it an update in knowledge when an observer receives information? Is it a useful rule for making predictions, rather than a literal description of reality changing? Different interpretations of quantum mechanics answer these questions in different ways. The experimental predictions are often the same, but the stories about what is happening underneath can differ sharply. One of the best-known approaches is the Copenhagen interpretation, associated especially with Niels Bohr and Werner Heisenberg. It emphasizes the practical role of measurement and the importance of describing experimental outcomes. In this view, quantum mechanics is primarily a tool for predicting the probabilities of what will be observed under specified conditions. Rather than insisting that every property has a definite classical value before measurement, the Copenhagen approach focuses on what can meaningfully be said in relation to an experimental setup. This made quantum mechanics extraordinarily useful, but it did not make every philosophical worry disappear. It allowed physicists to calculate, predict, and build experiments with remarkable success, while leaving some deeper questions partly unresolved. For many working scientists, that was acceptable. If the theory predicts the result and the result appears, the machinery is doing its job. Still, the question lingers quietly in the background. What is the world doing before the outcome is observed? Erwin Schrödinger sharpened that discomfort with his famous cat thought experiment in 1935. The point of Schrödinger's cat was not to suggest that cats normally spend their time hovering between life and death in cupboards, which would be both scientifically misleading and very unfair to cats. It was designed to expose the strangeness of applying quantum superposition to everyday objects. In the thought experiment, a cat is placed in a sealed box with a quantum event that could trigger a deadly mechanism. If the quantum system is treated as being in a superposition, then the whole setup seems to become entangled with that superposition. Taken too literally, the cat appears to be described as both alive and dead until the box is opened. Schrödinger intended this as a warning. He was showing that something deeply strange happens when the rules of microscopic quantum systems are stretched up toward ordinary experience. The thought experiment remains famous because it makes the measurement problem vivid. Tiny particles can be placed in superpositions. That much is experimentally supported. But the everyday world appears definite. Cats are not observed as misty blends of life and death. tables do not seem to occupy visibly combined positions. Detectors give particular readings. Reality at human scales has a stubborn habit of choosing one visible outcome. A modern idea that helps explain this is decoherence. Decoherence describes how quantum superpositions become effectively invisible when a system interacts with its environment. A delicate quantum system can maintain visible superposition only when it is isolated with great care. But large warm objects are constantly interacting with surrounding air molecules, photons, vibrations, heat, and countless other environmental influences. Those interactions rapidly spread quantum information into the environment. The different branches of the superposition stop being able to interfere with one another in any practical sense. Wojciech Zurek has been one of the important physicists in developing and explaining decoherence. The idea does not necessarily solve every aspect of the measurement problem because it does not by itself explain why one particular outcome is personally observed rather than another. But it does explain why the ordinary world looks classical. It shows how fragile quantum interference can be lost into the environment, making superpositions effectively unavailable at everyday scales. That is why a dust grain, a warm mug, or a cat is not observed in an obvious quantum blend of everyday states. The environment is constantly interacting with it. In a sense, the world is being monitored by everything around it: light, air, heat, surfaces, and fields. Not by consciousness in a mystical way, but by physical interaction. The universe is an extremely nosy neighbour, and it never stops gathering information. This is also why the word observation needs care. In quantum physics, observation does not mean a human mind must look at something. A measurement is a physical interaction that produces or records information about a system. A detector can measure. A photon can scatter. An environment can decohere a delicate state. Human awareness may enter later, but the physical process does not wait patiently for someone to lean over and say, "Interesting." So the real puzzle is not simply that quantum systems can exist in combined states. Superposition is strange, but it can be described and tested. The deeper puzzle is how definite experience arises from those possibilities. Quantum theory gives probabilities, measurements give outcomes. The bridge between those two facts is where interpretations begin, and where certainty becomes more difficult. Yet none of this makes quantum mechanics weak. Its predictions remain extraordinarily successful. The measurement problem is not a failure of the theory to work. It is a sign that the theory works so well that its meaning cannot be ignored. The world appears definite. Beneath that definiteness lies a mathematics of possibility. Somewhere between the two, measurement turns the soft landscape of what might happen into the single fact of what is found. A definite measurement gives one result, but quantum physics does not only change the meaning of observation, it also changes what can happen. Some events that classical physics would forbid outright become possible, not because nature has become careless, but because quantum objects are described by wave functions rather than tiny solid pellets following fixed paths. One of the clearest examples is quantum tunneling. In ordinary life, barriers behave rather sensibly. If a ball rolls toward a hill without enough energy to climb over it, the ball rolls back down. If a person walks into a locked door, the person remains on the same side of the door, perhaps with slightly reduced dignity. Classical physics treats energy barriers in a similar way. If a particle does not have enough energy to cross a barrier, then it should not appear on the other side. The barrier is too high. The particle is stuck. Quantum mechanics allows a stranger possibility. A particle can have a real probability of being found beyond an energy barrier, even when classical physics says it does not have enough energy to pass over the top. It does not smash through the barrier like a miniature cannonball. It has not secretly borrowed energy in a casual and suspicious way. Its wave function has behaved differently from a classical particle. The key is that a wave function does not always stop sharply at the edge of a forbidden region. When a quantum particle meets a barrier, the wave function can extend into the barrier, and, if the barrier is thin enough or the conditions are right, a small part of that wave function can extend beyond it. That means there is a non-zero probability of detecting the particle on the far side. The particle is tunnelled. This is not tunnelling in the everyday sense of digging a little passageway with a tiny shovel, although the image is admittedly appealing. Nothing has carved a hole through the barrier. The word tunnelling describes the result. A particle appears on the other side of something that classical mechanics says should have kept it trapped. One major natural example is alpha decay. Some radioactive atomic nuclei emit alpha particles, which are made of 2 protons and 2 neutrons. Inside the nucleus, the alpha particle can be held by the strong nuclear force, but it also faces an energy barrier caused by electric repulsion once it tries to escape. Classically, in many cases, the alpha particle should not have enough energy to get out. It should remain trapped inside the nucleus. Yet alpha decay happens. In the late 1920s, George Gamow used quantum tunneling to explain how alpha particles could escape atomic nuclei. The alpha particle's wave function could extend through the nuclear energy barrier, giving it a probability of appearing outside. Once outside, electric repulsion could push it away from the nucleus. This helped explain why some unstable nuclei decay at particular rates. The particle was not climbing over the barrier. It was doing something more quantum and less intuitive. It had a chance of being found beyond it. This made radioactive decay much more understandable. It also showed that tunneling was not just a laboratory curiosity. It was part of how certain atomic nuclei change over time. It is one reason some elements are unstable, why radioactive dating works, and why the deep interior of matter has its own quiet clockwork. Not clockwork in the old mechanical sense, but a probability-driven quantum clockwork, which is somehow both more subtle and more alarming. Tunneling is also essential to real technology. One of the clearest examples is the scanning tunneling microscope. This instrument can image surfaces at atomic scales by using the tunneling of electrons between a very sharp conducting tip and a surface. The tip is brought extremely close to the material, so close that the gap is only on the scale of atoms. Classically, electrons should not simply cross that empty gap if they lack the required energy, but quantum mechanically their wave functions can extend across it, allowing a tunneling current to flow. That current is incredibly sensitive to distance. Even a tiny change in the gap between the tip and the surface changes the tunneling current noticeably. By scanning the tip across the surface and measuring those changes, scientists can map the arrangement of atoms. The scanning tunneling microscope, developed by Gerd Binnig and Heinrich Rohrer in the early 1980s, opened a way to see and manipulate matter at a scale that once belonged almost entirely to theory. Tunneling, in other words, helps turn the strange behavior of wave functions into an actual picture of the atomic world. Stars also rely on tunneling. In the cores of stars like the Sun, nuclear fusion occurs when light atomic nuclei combine to form heavier nuclei releasing energy. But positively charged nuclei repel each other because of the electromagnetic force. To fuse, they must get extremely close enough for the strong nuclear force to take over. The temperatures and pressures in stellar cores are immense, but even there, classical physics alone would make fusion much harder to sustain at the observed rate. Quantum tunneling helps particles overcome the electric repulsion between them. Hydrogen nuclei in the Sun do not simply stroll together politely and agree to become helium. They resist each other because both are positively charged, but their wave functions allow a small probability of getting close enough for fusion to occur. That small probability matters enormously because the Sun contains a vast number of particles. Even rare events become powerful when the numbers are stellar. The sunlight reaching Earth is connected in part to quantum tunneling deep inside the Sun. This is one of the quiet surprises of tunneling. It's not confined to strange apparatus or rare radioactive atoms. It is tied to the light of stars, the behavior of nuclei, and the ability to image individual atoms. A process that sounds almost impossible helps make the universe visible. Tunneling also shows why probability in quantum physics is not merely about what is known, it is about what is physically allowed. Classical mechanics would draw a hard line and say the particle cannot cross. Quantum mechanics gives a probability, sometimes tiny, sometimes useful, sometimes essential. The barrier is still real, the particle is still constrained. But the wave function changes the meaning of impossible. This does not mean anything can pass through anything at any time. Tunneling probabilities usually fall rapidly when barriers are thick, wide, or high. A person does have a quantum wave function in principle, but the chance of a person tunneling through a wall is so fantastically small that it is functionally zero. Waiting for it would be a poor use of an evening, even a very patient one. At microscopic scales, though, the effect is real. Alpha particles escape nuclei. Electrons tunnel across tiny gaps. Fusion happens in stars. Quantum mechanics does not erase barriers, but it softens the absolute certainty that classical physics placed around them. A particle described by a wave function does not meet the world as a little hard bead moving through fixed corridors. Its possibilities can extend into regions that classical thinking would close off completely. And sometimes, when measurement finally gives an answer, the particle is found on the far side. Quantum tunneling shows that particles are not tiny hard beads moving through a world of perfectly absolute barriers. Their wave functions can extend, fade, and sometimes leave a particle with a real probability of appearing where classical physics says it should not be. But quantum physics does more than allow particles to pass through barriers. It also explains why matter does not collapse into a featureless crush. That brings us to spin. Spin is one of those words in physics that is both useful and slightly dangerous. It suggests an image of a tiny ball rotating in space, like a miniature planet turning on its axis. But quantum spin is not quite that. Particles such as electrons do have an intrinsic kind of angular momentum, and this property affects how they behave in magnetic fields, how they combine with other particles, and how atoms are structured. Yet an electron is not a little sphere visibly whirling around. Spin is built into the particle itself. It is one of its basic quantum properties, like charge or mass. This matters because quantum particles are not all alike in the way they follow rules. Some particles belong to a family called fermions. Electrons, protons, and neutrons are fermions. Other particles, such as photons, belong to a different family called bosons. Fermions have a special kind of spin, and because of this they obey one of the most important rules in all of physics, the Pauli exclusion principle. Wolfgang Pauli introduced this principle in 1925. In simple terms, it says that no two identical fermions can occupy the exact same quantum state at the same time. That phrase sounds technical, but the meaning is profound. Electrons cannot all pile into the lowest possible state around an atom. They have to arrange themselves into different available states. Nature, at this level, has a seating plan. It is not always polite, but it is extremely strict. This is one of the main reasons atoms have structure. Imagine for a moment if electrons did not obey the Pauli exclusion principle. In that case, they could all fall into the lowest energy state around the nucleus. The rich layered architecture of atoms would vanish. The periodic table would not have its familiar shape. Chemistry would lose the pattern that allows carbon, oxygen, nitrogen, iron, gold, and all the other elements to have their distinctive behaviours. Matter would not build itself into the varied world of minerals, oceans, air, cells, forests, and people, quietly wondering where they left their keys. Because electrons are fermions, they fill atomic orbitals in an ordered way. Each orbital can hold only a limited number of electrons with compatible quantum properties. This produces electron shells and subshells. The arrangement of these electrons determines how atoms bond, which reactions they take part in, and why elements in the same column of the periodic table often share similar chemical behaviour. The periodic table is not just a chart of elements. It is a visible map of quantum rules. Spin is part of that map. Electrons can pair in an orbital only when their spin states differ in the allowed way. This is why the idea of spin is not a decorative detail. It helps shape chemistry itself. The difference between a reactive metal, a noble gas, and an atom ready to form strong covalent bonds depends on how electrons are arranged, and that arrangement depends on quantum states, spin, and exclusion. The deeper statistical rules for fermions were developed by Enrico Fermi and Paul Dirac. Fermi-Dirac statistics describe how collections of identical fermions behave. The essential idea, without diving into the mathematics, is that fermions resist being crowded into the same state. Unlike bosons, which can gather into the same quantum state under the right conditions, fermions are forced to spread across available states. They do not all get to sit in the same lowest energy chair. Pauli has already reserved the seating, and he is not taking complaints. This resistance to crowding is not just important inside atoms. It also helps explain the stability of matter more generally. Ordinary objects have volume partly because the electrons in neighbouring atoms cannot all be compressed into identical states. There are electromagnetic repulsions between electrons as well, but the Pauli exclusion principle adds a deeper quantum reason why matter resists being squeezed into nothing. Solidity is not merely little particles bumping against each other like tiny marbles. It is the large-scale result of quantum rules operating with relentless consistency. At human scales, this feels completely ordinary. A hand rests on a table, and the table pushes back. A stone holds its shape. A floor does not allow a person to drift through it into the room below, which is usually convenient. But beneath that everyday solidity is a complicated quantum structure. The electrons in atoms and molecules occupy allowed states. Their wave functions arrange according to quantum rules. The Pauli exclusion principle prevents identical fermions from collapsing into the same state. The same principle becomes even more dramatic in extreme astrophysical objects. In white dwarfs, the dense remnants of stars like the Sun, matter is packed so tightly that ordinary atomic structure is largely crushed. What helps support a white dwarf against further collapse is electron degeneracy pressure, which arises from the Pauli exclusion principle. The electrons cannot all occupy the same low-energy states, so they generate a pressure that resists gravity. In neutron stars, the situation becomes still more extreme. These objects form after the collapse of massive stars, when matter is compressed to astonishing densities. A neutron star can contain more mass than the Sun packed into a sphere only about the size of a city. There, neutron degeneracy pressure, along with the strong nuclear force and other effects, helps resist further collapse. The same underlying quantum refusal to share identical states helps shape some of the densest known objects in the universe. This is one of the quiet triumphs of quantum physics. A principle introduced to explain atomic behavior also helps describe stellar remnants. The rules that arrange electrons around a nucleus echo upward into the lives and deaths of stars. The small and the cosmic are not separate stories. They're connected through the same deep structure. Spin and the Pauli exclusion principle show that quantum physics is not only about strange experiments involving slits, detectors, or particles appearing beyond barriers. It is also about why matter has form. Atoms have shells because electrons obey exclusion. Elements have chemical personalities because electrons fill orbitals in ordered patterns. Objects have volume because matter resists being compressed into identical quantum states. White dwarfs and neutron stars exist because even under immense gravity, fermions still follow their rules. The world feels solid because the quantum world is disciplined. Beneath the surface of every object, from a grain of salt to a distant stellar remnant, particles are not simply occupying space like tiny classical pieces. They are obeying precise quantum restrictions. Matter has shape because not everything is allowed to be the same, in the same place, in the same state, all at once. The Pauli exclusion principle shows that quantum particles do not simply behave as separate little objects, each carrying its own private set of ordinary properties. Their identities, states, and arrangements can depend on rules that have no easy everyday equivalent. But there is an even deeper challenge waiting inside quantum physics, one that troubled Albert Einstein more than almost anything else in the theory. It is called entanglement. Quantum entanglement occurs when two or more particles must be described together, even if they are separated by a large distance. Their properties are not fully independent in the classical sense. The combined system has one shared quantum state, and measurements made on one part can be strongly correlated with measurements made on the other. This does not mean the particles are joined by a tiny invisible string, or whispering instructions across space like very disciplined spies. It means the quantum description belongs to the pair as a whole. That idea deeply bothered Einstein. In 1935, Einstein worked with Boris Podolsky and Nathan Rosen on a famous argument now known as the EPR paradox. The initials come from their surnames, and the argument was meant to show that quantum mechanics might be incomplete. Einstein, Podolsky, and Rosen considered situations where particles interact, separate, and then remain connected in the mathematical description. Measuring one particle could allow a physicist to predict something about the other, even if the other particle was far away. Einstein objected because this seemed to challenge two ideas he valued strongly. One was locality, the idea that objects should be directly influenced only by their immediate surroundings, with no instant physical influence leaping across space faster than light. The other was realism, roughly the idea that physical properties should have definite values independent of whether anyone measures them. Quantum mechanics seemed to threaten at least one of these comforting principles, and possibly both. Einstein famously criticized the situation as spooky action at a distance. The phrase is often repeated because it is wonderfully memorable, but it needs care. Einstein was not endorsing spooky action. He was objecting to what he thought quantum mechanics implied. He believed the theory might be missing deeper hidden information that would restore a more complete and local picture of reality. In his view, quantum mechanics worked astonishingly well, but perhaps it did not describe the whole underlying story. For a long time, this looked like a philosophical disagreement. One side could say quantum mechanics was complete enough. Another could suspect hidden variables beneath it. The experimental predictions available at the time did not seem to force the issue cleanly. Physics had a puzzle with deep consequences, but no obvious way to make nature answer. Then John Bell changed the situation. In the 1960s, Bell developed what is now called Bell's theorem. It showed that the disagreement was not merely philosophical after all. Certain kinds of hidden variable theories, especially simple local hidden variable theories, would predict limits on the correlations between measurements of entangled particles. Quantum mechanics predicted that those limits could be violated. In other words, the question could be tested. nature could be asked whether it obeyed the restrictions expected from a local hidden variable picture, or whether it followed the stronger correlations predicted by quantum theory. This was a remarkable turn. A debate about the meaning of reality became an experimental question. Later experiments tested Bell's inequalities using entangled particles. Alain Aspect and his colleagues carried out especially important tests in the early 1980s, measuring correlations between entangled photons. The results supported the predictions of quantum mechanics. Since then, many increasingly refined experiments have been performed, including loophole-reducing Bell tests designed to close possible gaps in the earlier setups. Again and again, quantum predictions have been supported over simple, local hidden variable models. This does not mean every interpretation question is settled. Physicists and philosophers still debate what quantum mechanics is telling us about reality. But the experiments have made one thing very difficult to maintain: the idea that entangled particles are merely carrying ordinary, pre-written local instructions that fully explain the observed correlations. The world appears to be stranger than that. Entanglement also needs one very important clarification. It does not allow faster-than-light messaging. This is often misunderstood. If two particles are entangled and far apart, measuring one is correlated with measuring the other. But the result of each individual measurement is not controllable in a way that can be used to send a message instantly. One observer cannot choose a result on one side and use it to transmit information to the other side faster than light. The correlations only become clear when the results are later compared through ordinary communication, which still obeys the speed limit set by relativity. So entanglement is not a cosmic telephone with no delay. It is not a way to send tomorrow's lottery numbers across the galaxy, which is probably for the best because the administrative consequences would be dreadful. It is a profound relationship between quantum systems, not a practical loophole for instant communication. Still, the relationship is astonishing. Two particles can be separated by enormous distances, yet the correct quantum description treats their measured properties as linked. The separateness that seems so obvious in everyday life becomes less straightforward. In classical thinking, once two objects move apart, each object carries its own complete set of properties. One glove in a box may be left-handed, and the matching glove far away may be right-handed. Opening one box reveals what was already true about the other. Entanglement is not merely like that. The correlations can be stronger than any ordinary hidden instruction story allows. This connects directly to measurement. Quantum physics had already shown that measurement does not simply uncover a world of tiny classical facts waiting neatly underneath. With entanglement, the challenge becomes even sharper. It is not only unclear what a particle is doing before observation, it is also unclear whether widely separated particles can always be treated as fully independent things with properties belonging only to themselves. At the human scale, the world still looks comfortably separated. A cup is on the table, a lamp is across the room, a moon is far from Earth. Ordinary objects have locations, boundaries, and independent histories. But beneath that familiar picture, quantum systems can share states in ways that ignore the simple separateness of everyday intuition. Entanglement does not make the universe magical. It makes it precise in a way that common sense did not anticipate. Measurements on entangled particles follow statistical patterns that can be tested, repeated, and used in emerging technologies such as quantum cryptography and quantum computing. The strangeness is not decorative. It is operational. It does work. Einstein was right to be disturbed by the implications, even though the experiments have not supported the simple local hidden variable picture he hoped might exist. His discomfort helped sharpen the question, and Bell's theorem helped turn that question into one of the most beautiful tests in modern physics. Quantum physics had already challenged particles, paths, positions, and possibilities, Entanglement challenges separateness itself. It suggests that the deep description of reality may not always be built from isolated pieces with private properties, but from relationships that only reveal their full meaning when the system is considered as a whole. Entanglement makes it difficult to think of the universe as a collection of separate little things, each carrying its own private properties through empty space. Quantum physics keeps suggesting that the deeper story is less like a pile of tiny beads and more like a web of relationships, states, and possibilities. To move closer to the modern picture, the idea of a particle itself has to change again. This is where quantum field theory enters. Quantum field theory is the framework that brings quantum mechanics together with special relativity. Special relativity, developed by Albert Einstein in 1905, showed that space and time are linked, and that no influence or information can travel faster than light in vacuum. Quantum mechanics described the behavior of atoms, photons, electrons, and probabilities. Both theories were astonishingly successful, but they had to be made to work together. Particles could not simply be treated as little classical objects if they were moving at high speeds, being created, being destroyed, or interacting through fields. Quantum field theory offers a deeper language. It treats particles as excitations of underlying fields. A field in physics is something that has a value throughout space and time. A familiar example is the electromagnetic field. Even when no charged particle is sitting in a particular spot, the field concept still allows physics to describe how electric and magnetic influences exist and change. Quantum field theory extends this kind of thinking. Instead of imagining the universe as empty space containing little particles, it describes space as filled with fields. Each type of particle is associated with its own field. An electron in this picture is not best understood as a tiny bead moving through nothingness. It is an excitation of the electron field. It has properties such as electric charge, mass, and spin, not because it is a little object with tiny parts inside it, but because those are the properties of that kind of quantum excitation. A photon is an excitation of the electromagnetic field. Other particles are excitations of other fields. The particle is real, but it is not a tiny marble in the old classical sense. It is more like a localized ripple in something deeper, though even that image is only a guide, not a perfect picture. This shift helps explain why particles of the same type are truly identical. Every electron in the universe has the same charge and the same basic mass, because every electron is an excitation of the same electron field. Electrons are not manufactured individually with matching specifications, like nature running a very precise but rather secretive factory. They are manifestations of one underlying field, appearing in different places and conditions. One of the key steps toward this modern view came from Paul Dirac. In the late 1920s, Dirac developed a relativistic equation for the electron, bringing quantum mechanics into agreement with special relativity in a new and powerful way. His equation did something remarkable. It predicted the existence of antimatter. More specifically, it implied a particle like the electron but with positive electric charge. That particle, the positron, was discovered by Carl Anderson in cosmic ray observations in 1932. Cosmic rays are high-energy particles arriving from space, and when they strike Earth's atmosphere or pass through detectors, they can reveal new particle behavior. Anderson's discovery confirmed that Dirac's mathematics had pointed towards something real. Antimatter was not just a strange feature of an equation, it existed in the physical universe. Quantum field theory also provided the foundation for quantum electrodynamics, often called QED. This is the quantum theory of light and electrically charged particles. It describes how electrons and photons interact. It explains processes such as the emission and absorption of light, the scattering of particles, and the subtle corrections that arise from quantum fields. Several physicists played central roles in building quantum electrodynamics into its modern form. Richard Feynman developed a famously visual and practical approach using diagrams that represent possible interactions. Julian Schwinger and Shinichiro Tomonaga developed powerful mathematical formulations. Freeman Dyson helped show how these different approaches were connected. The result was one of the most successful theories in the history of science. The precision of quantum electrodynamics is almost absurdly good. One famous example is the electron's magnetic moment, a property connected to how the electron behaves in a magnetic field. Quantum electrodynamics predicts this value with extraordinary accuracy, matching experimental measurements to an astonishing number of decimal places. The details involve difficult mathematics, but the meaning is simple enough. The theory looks strange, but it works with breathtaking precision. This is an important point to hold on to. Quantum field theory can sound abstract, almost dreamlike. Fields filling space, particles as excitations, empty space not quite empty, interactions described by probabilities and virtual processes. It would be easy to mistake all this for speculation if it were not so tightly anchored to experiment. The theory earns its place because it predicts what nature actually does. Quantum fields also help connect earlier ideas. Photons, which first appeared as light arriving in packets, become excitations of the electromagnetic field. Electrons, once imagined as tiny particles orbiting nuclei, become excitations of the electron field. Entanglement becomes less like a mysterious thread between separate beads, and more like a feature of quantum states that can belong to systems spread across space. The old image of isolated particles travelling through a blank background begins to fade. Space itself becomes more structured. This does not mean that fields are easy to picture. They're not simply invisible fluids filling the universe. They are mathematical and physical entities, described by rules that combine quantum mechanics, relativity, symmetry, and conservation laws. But they allow modern physics to explain particle creation and destruction, antimatter, electromagnetic interactions, and the behavior of matter at very small scales. The everyday world still looks like it is made of things, and in a practical sense it is. Tables, stones, lamps, and hands are not illusions. But underneath them, the word thing becomes less straightforward. Matter is built from particles, and particles are excitations of fields. Solidity comes from quantum states and forces. Light comes from the electromagnetic field. The vacuum itself begins to look less like absolute emptiness, and more like the lowest energy condition of fields that fill all of space. Quantum field theory does not make the universe less real. It makes reality deeper than the older picture allowed. The world is not merely tiny objects moving through empty space. It is fields, excitations, interactions, probabilities and measurements woven together into the calm appearance of ordinary matter. A photon crossing a room, an electron in an atom, and an entangled pair separated across a laboratory are all part of this larger field-based description. Modern quantum physics is not only about particles, it is about the hidden structures from which particles arise and the strange, precise fields that make empty space feel far less empty than it first appears. Once particles are understood as excitations of fields, empty space begins to look different. In the older, more familiar picture, a vacuum means nothing is there. Remove the air from a container, take away the dust, block the light, and what remains seems to be emptiness. It is the absence of stuff, a blank stage, a silent room with no actors, no furniture, and no one coughing politely in the back row. But quantum field theory changes that picture. In modern physics, the quantum vacuum is not simple nothingness. It is the lowest energy state of quantum fields, That phrase matters. A vacuum is not a place where fields have disappeared. The fields are still there. The electromagnetic field is still there. The electron field is still there. Other quantum fields are still part of the description of space. What the vacuum means is that these fields are in their lowest available energy condition. Lowest energy does not mean no activity at all. Quantum fields cannot always be perfectly still in the classical sense. Their values have unavoidable uncertainties because quantum mechanics does not allow certain properties to be fixed with unlimited precision. This leads to what physicists call vacuum fluctuations. Vacuum fluctuations are often described carelessly, as if particles are constantly popping into existence from nowhere and then vanishing again like tiny stage magicians with very short contracts. That image can be memorable, but it is also misleading if taken too literally. The quantum vacuum is not full of ordinary particles appearing as fully real little objects and then diving behind the curtain. Real particles are measurable excitations of fields. Vacuum fluctuations are better understood as fluctuations in the underlying quantum fields, part of the mathematical and physical structure of the lowest energy state. This distinction is important because it keeps the idea grounded. The quantum vacuum is strange, but it is not a magic cupboard. It does not mean energy can be pulled freely from empty space to power a kettle, a spaceship, or a suspicious machine advertised with too many exclamation marks. The vacuum has measurable effects in physics, but those effects obey strict rules. One famous example connected to vacuum field behavior is the Casimir effect. In 1948, Hendrik Casimir predicted that two uncharged conducting plates placed extremely close together in a vacuum would experience a tiny attractive force. The basic idea is that the presence of the plates changes which electromagnetic field modes can exist between them compared with outside them. This difference leads to a small force pushing the plates together. The Casimir effect is subtle. It's not a dramatic blast from the void. The plates have to be extremely close, usually separated by distances far smaller than a human hair, before the effect becomes noticeable. But the importance of the Casimir effect is that it shows the vacuum is not merely a blank absence. The allowed behavior of quantum fields in empty space can be changed by boundaries, and that change can have physical consequences. Another important clue comes from the Lamb shift. In the 1940s, Willis Lamb and Robert Rutherford measured a tiny difference in energy levels in hydrogen that earlier theory had not fully accounted for. Hydrogen is the simplest atom, with one proton and one electron, which makes it an ideal testing ground for precise physics. Quantum electrodynamics explained the Lamb shift by taking into account the interaction between the electron and the quantum electromagnetic field, including effects connected to vacuum fluctuations. This was not a large everyday effect. Nobody notices the Lamb shift while making toast, but in precision atomic physics, it mattered enormously. It showed that the quantum vacuum and the field-based description of reality could subtly affect atomic energy levels. The empty space around an electron was not just a passive backdrop, it was part of the calculation, and the calculation matched experiment. This is one of the reasons quantum electrodynamics became so respected. It didn't merely describe broad ideas, it explained delicate details. Tiny corrections, almost unimaginably small by ordinary standards, could be measured and predicted. The quantum vacuum entered physics not as an aesthetic preference, but because its effects appeared in careful experiments. The quantum vacuum also matters in particle physics and cosmology. In particle physics, vacuum states are tied to how fields behave, how particles acquire properties, and how interactions are understood. In cosmology, vacuum energy is part of discussions about dark energy and the expansion of the universe, although the relationship between quantum vacuum energy and the observed cosmological constant remains one of the most difficult unresolved problems in theoretical physics. That unresolved difficulty should be stated clearly. The quantum vacuum is important, but it is not a simple explanation for every mystery. Popular accounts sometimes stretch the idea too far, turning vacuum energy into a universal answer or a source of unlimited power. Real physics is more restrained. It says the vacuum has structure. It says fields remain present even in their lowest energy state. It says measurable effects can arise from this structure. It does not say that empty space is a free battery waiting for someone with a garage prototype and dramatic lighting. The word empty has therefore become more subtle. A region of space can contain no ordinary particles and still not be absolute nothingness. It can be in a vacuum state, with quantum fields present and capable of fluctuations. Its properties can influence forces between plates, tiny shifts in atomic spectra, and the behavior of particles at high precision. This connects directly to the field picture of particles. If particles are excitations of fields, then the absence of particles does not mean the absence of fields. A calm ocean with no visible waves is still an ocean. That comparison is imperfect, because quantum fields are not ordinary fluids, but it helps point in the right direction. No visible ripple does not mean no underlying medium of description. The fields remain part of space, even when no particle excitation is present. The quantum vacuum is not a theatrical nothing. It is the quietest condition of something. And that may be one of the strangest lessons of quantum physics. The world is not built from objects sitting inside an empty container. It is built from fields, states, interactions, and probabilities. Even when all visible matter is removed, the underlying structure does not simply vanish. Space itself has become part of the physical story. Empty space, in the quantum view, is not truly empty. It is simply as quiet as the fields are allowed to be. The quantum vacuum may sound distant from ordinary life, as if it belongs only to particle accelerators, equations, and the quiet spaces between stars. But quantum physics is not locked away in the far corners of reality. It is also inside every breath, every colour, every chemical bond, every warm meal, every leaf, every stone, and every living cell. The reason is simple, but enormous. Chemistry is quantum physics in everyday clothing. Atoms do not join together at random. Their behaviour is shaped by electrons, and electrons obey quantum rules. They occupy orbitals, not little classical tracks. They have allowed energy states. They follow the Pauli exclusion principle. They form patterns around atomic nuclei that determine how atoms attract, repel, share, and exchange. The world of chemistry, with all its familiar substances and reactions, rests on the hidden arrangement of electrons. A carbon atom behaves like carbon because of its electron structure. Oxygen behaves like oxygen for the same reason. Sodium is reactive, chlorine is reactive in a very different way, and together they form sodium chloride, ordinary table salt, because their electrons can rearrange into a more stable pattern. This is not just a tidy chemical story, it is a quantum story. The rules governing electron orbitals and energy levels decide which atoms bond, how strongly they bond, what shapes molecules take, and how much energy is absorbed or released when reactions happen. Chemical bonding depends on quantum mechanics. In a covalent bond, atoms share electrons. But that sharing is not like two neighbours politely passing a spoon across a fence. The electrons are described by wave functions that spread across more than one nucleus. The bond forms because the combined quantum state of the electrons and nuclei can be lower in energy than the separated atoms. Molecules are stable when their quantum arrangements make stability possible. This is why molecular shapes are so specific. Water is bent rather than straight. Carbon dioxide is linear. Methane forms a tetrahedral shape. with hydrogen atoms arranged around carbon in a balanced three-dimensional pattern. These shapes are not decorative. They affect boiling points, melting points, solubility, smell, taste, reactivity, and biology. The shape of a molecule helps decide what it can do, what it can bind to, and how it behaves inside living systems. Linus Pauling was one of the great figures in bringing quantum ideas into chemistry. His work helped explain covalent bonding, molecular structure, hybrid orbitals, and the nature of chemical bonds in a way that connected laboratory chemistry to quantum mechanics. Pauling showed that the shapes and strengths of bonds could be understood through the behavior of electrons, not as tiny hard pieces, but as quantum objects described by orbitals and shared states. Quantum chemistry turned chemistry from a collection of useful rules into something rooted more deeply in physics. The periodic table also becomes more meaningful through quantum mechanics. Elements are arranged by atomic number, but the repeating patterns in their chemical behavior arise because electrons fill shells and subshells in a structured way. The noble gases are mostly unreactive because their outer electron shells are filled in a stable arrangement. The alkali metals are reactive because they have a single outer electron that can be lost relatively easily. The halogens are reactive because they are close to filling their outer shell and readily gain or share electrons. The familiar columns of the periodic table are in effect columns of quantum behavior. Color, too, is often quantum physics made visible. When light strikes a material, photons can be absorbed if their energies match the differences between allowed energy levels in atoms, molecules, or solids. If certain wavelengths are absorbed and others are reflected or transmitted, the material takes on color. A pigment looks red because it absorbs some parts of visible light more strongly and reflects or transmits others. A leaf looks green because chlorophyll absorbs red and blue light strongly, while reflecting more green light. A gemstone gets its color from the way its crystal structure and trace impurities affect the energy levels available to electrons. Ruby is a beautiful example. Pure aluminium oxide is colorless, but when small amounts of chromium are present, the energy levels associated with the chromium ions allow certain wavelengths of light to be absorbed. The remaining transmitted and reflected light gives ruby its deep red appearance. Sapphire, emerald, and many other gemstones also owe their colors to quantum interactions between light, electrons, impurities, and crystal fields. The sparkle may be romantic, but the color is doing serious physics in a very elegant outfit. Semiconductors offer another clear case. In materials such as silicon, electrons occupy energy bands rather than isolated atomic levels. The gap between these bands helps determine how the material conducts electricity and how it interacts with light. In light-emitting diodes, electrons move between energy states and release photons. The color of the light depends on the energy difference involved. Red, green, blue, and white LED lights are all connected to quantum energy levels in solid materials. Modern screens, solar cells, cameras, computer chips, and optical communications all depend on this quantum behavior. Life also obeys quantum rules, because life is chemistry, organized with astonishing complexity. Proteins, DNA, cell membranes, sugars, fats, enzymes, and pigments are all made of atoms and molecules. Their structures and reactions depend on electron behavior, chemical bonds, energy levels, and molecular shapes. There is no separate non-quantum chemistry inside biology. Living things do not step outside physics just because they are damp and complicated. At the same time, this needs care. Quantum physics does not mean that every mystery in biology is explained by vague quantum magic. It does not currently explain consciousness in any simple confirmed way, and it should not be used as decorative fog around ideas that lack evidence. The brain obeys physics, of course, and neurons are made of atoms and molecules. but saying that is not the same as proving that consciousness depends on exotic quantum superpositions. Biology is already wondrous enough without adding unsupported glitter. There are, however, grounded places where quantum affects matter in life. Photosynthesis is one of them. In plants, algae, and some bacteria, light is absorbed by pigment molecules, and that energy is transferred through molecular structures toward reaction centers where chemical energy can be stored. Researchers have studied whether quantum coherence may help describe aspects of this energy transfer under some conditions. The details are subtle and not a cartoon of leaves doing quantum wizardry, but the broader point is clear. The absorption of photons, the movement of excitation energy, and the chemical reactions that store sunlight all depend on quantum physics. Enzyme reactions offer another example. Enzymes are biological catalysts. They help chemical reactions happen faster by lowering the energy barrier between reactants and products. In some enzyme-catalyzed reactions, quantum tunneling may play a role, especially for tiny particles such as electrons or hydrogen nuclei moving through energy barriers. This does not make enzymes magical. It means that the same quantum principles seen in nuclear decay and tunneling microscopes can also appear in carefully specific ways inside the chemistry of life. Even breathing has a quantum foundation. Oxygen binds to hemoglobin because of molecular structure, electron arrangements, and chemical affinity. Food releases energy through reactions involving electrons moving between molecules. Nerves function through electrical and chemical changes across cell membranes, ultimately dependent on ions, molecular channels, and electromagnetic interactions. Vision begins when photons are absorbed by molecules in the retina, changing their shape and triggering a biochemical signal. Every sensation of color begins with quantum energy meeting living chemistry. The everyday world therefore becomes less ordinary, not because it stops being familiar, but because its familiarity is supported by hidden precision. Bread browns because molecules react and rearrange. Metal shines because electrons in the solid interact with light. Soap cleans because molecular structures interact differently with water and oils. A flower has color because photons and pigments exchange energy in specific ways. A battery works because chemical energy can be converted into electrical energy through electron transfers. Quantum physics is not a remote layer beneath life. It is the reason chemistry has rules at all. It gives atoms their structures, molecules their shapes, materials their colors, and reactions their energy pathways. It explains why matter can be stable and varied, why elements repeat in patterns, and why complex molecules can form the delicate machinery of living cells. The abstract ideas of wave functions, orbitals, energy levels, spin, exclusion, photons, and tunneling all return here in quieter forms. They become the taste of salt, the green of leaves, the red of ruby, the glow of a screen, the warmth of food, and the breath moving gently in and out of the body. Quantum physics may seem strange when first encountered, but it is not separate from the ordinary world. It is one of the reasons the ordinary world is possible. Quantum physics may begin with glowing objects, electrons, photons, and wave functions, but it does not remain politely tucked away inside textbooks. It has become one of the practical foundations of modern civilization. The same ideas that once made physicists argue about light, atoms, and measurement now help run computers, guide aircraft, scan groceries, measure time, carry internet signals, and build machines that would have sounded almost fictional a century ago. A good place to begin is the laser. A laser produces light that is highly organized. Ordinary light from a lamp contains many wavelengths and directions jumbled together. Laser light is coherent, meaning its waves are aligned in a carefully ordered way. This gives lasers their narrow beams, precise focus, and usefulness in everything from barcode scanners and fiber optic communication to eye surgery and scientific instruments. The key quantum idea behind lasers is stimulated emission. Albert Einstein described the theoretical basis for stimulated emission in 1917. In simple terms, an atom or molecule in an excited energy state can be encouraged by an incoming photon to release another photon with the same energy, direction, and phase. Instead of light being emitted randomly, the process can amplify a coordinated beam. It is like persuading a crowd to hum the same note at the same time, although atoms are usually better at staying in tune than crowds. The first practical laser was built by Theodore Maiman in 1960 using a ruby crystal. That achievement turned a quantum principle into a working technology. Since then, lasers have become so common that they can feel almost ordinary, which is slightly unfair to them. A laser pointer may look simple, but it is a small and neat demonstration of atoms, photons, and quantum energy levels behaving with exquisite discipline. Modern electronics also depend directly on quantum physics. Semiconductors, especially silicon, work because electrons in solids occupy energy bands. These bands determine whether a material acts like a conductor, an insulator, or something in between. A semiconductor can be controlled because its electron behavior can be carefully adjusted by adding tiny amounts of other elements, a process called doping, and by applying electric fields. Transistors use this controlled electron behavior to switch and amplify signals. A modern computer chip contains billions of transistors, each one relying on the quantum properties of electrons in solid materials. The result is modern computing. Phones, laptops, satellites, cameras, medical devices, and much of the internet rest on this quantum foundation. The digital world may feel clean and abstract on a screen, but underneath it are electrons moving through materials according to rules discovered by quantum physics. Timekeeping has also become quantum. Atomic clocks use precise transitions between energy states in atoms to measure time. Cesium atomic clocks are especially important, because the official definition of the second is based on a particular transition in cesium atoms. These clocks are extraordinarily stable. They allow navigation systems, telecommunications, financial networks, power grids, and scientific measurements to stay synchronized. A navigation signal depends on time so precise that tiny errors can become large position errors. If timekeeping drifts, location drifts with it. This means that quantum transitions inside atoms help people find their way through cities, across oceans, and above the clouds. The quiet regularity of atomic energy levels supports the noisy practical world of maps, phones, aircraft, and delivery vans. There is something pleasing about that. The universe's smallest rules help stop people from taking the wrong motorway exit, although they cannot yet prevent anyone from insisting they knew the way all along. Quantum computing takes the practical story into a more experimental and rapidly developing direction. A classical computer uses bits, which represent definite states. A quantum computer uses qubits. A qubit can be prepared in a superposition of possible states, and multiple qubits can be entangled. Quantum algorithms can use superposition, entanglement, and interference to process certain kinds of problems in ways that differ from ordinary computing. This does not mean a quantum computer is simply a faster laptop. It is not a magical upgrade that makes every spreadsheet, video game, or forgotten password instantly surrender. Quantum computers are expected to be especially useful for certain specific tasks, such as simulating quantum systems, exploring some optimization problems, and attacking particular mathematical problems. Their power is specialized, not universal. Peter Shor developed Shor's algorithm, which showed that a sufficiently powerful quantum computer could factor large numbers far more efficiently than known classical methods, with major implications for some forms of cryptography. Love Grover developed Grover's algorithm, which offers a quantum speed-up for searching unsorted data. These algorithms helped reveal that quantum computation was not just an interesting thought experiment, but a serious new model of information processing. Institutions and companies such as IBM, Google Quantum AI, and the National Institute of Standards and Technology have played visible roles in quantum technology, from building experimental quantum processors to developing standards, measurements, and research programs. Much of the field remains challenging. Qubits are delicate. They are disturbed easily by noise, heat, and unwanted interactions with the environment. Building reliable quantum computers requires error correction, careful engineering, and extremely controlled physical systems. Even with those difficulties, the direction is clear. Quantum physics is not only an interpretation of microscopic reality, it is a working toolbox. It gives us lasers, semiconductors, transistors, atomic clocks, sensors, and the early foundations of quantum computing. It shapes the devices that shape daily life. The strange rules beneath matter do not stay strange forever. With enough understanding, they become technology. The photon becomes a laser beam. The electron becomes a transistor. The atomic transition becomes a clock. The superposition becomes a qubit. Quietly, patiently, the quantum world has become part of the machinery of the modern age. Quantum physics has explained an astonishing amount of the world. It describes the behavior of atoms, the structure of molecules, the colors of materials, the working of lasers, the logic of transistors, and the precision of atomic clocks. It reaches into chemistry, biology, electronics, and the light of stars. It is not a fringe theory resting on delicate speculation. It is one of the most successful frameworks science has ever built. And yet, at the edge of this success, there is still a boundary. That boundary is gravity. Quantum mechanics works extraordinarily well for particles, atoms, fields, and the small-scale structure of matter. General relativity works extraordinarily well for gravity, space-time, planets, stars, galaxies, and the large-scale structure of the universe. Each theory has been tested again and again in its own domain. Each has survived with remarkable strength. But when physicists try to combine them completely, the result is not yet a finished theory. Albert Einstein's general theory of relativity, published in 1915, changed the meaning of gravity. In Newton's older picture, gravity was a force acting between masses. The sun pulled on Earth. Earth pulled on the moon. Apples fell because Earth attracted them downward. Newton's theory worked with extraordinary accuracy for many purposes, and still does in everyday settings. Einstein's theory went deeper. General relativity describes gravity not as an ordinary force in the usual sense, but as the curvature of space-time. Matter and energy tell space-time how to curve, and curved space-time tells matter how to move. A planet orbiting the sun is not being tugged through a perfectly flat stage. It is following a path through curved space-time created by the sun's mass and energy. This idea has been confirmed in many ways. It explains the bending of light by gravity, the shift in Mercury's orbit, the slowing of time in gravitational fields, and the gravitational waves detected by the Laser Interferometer Gravitational Wave Observatory. General relativity is not a loose metaphor. It is a precise and powerful theory of gravity. The difficulty is that general relativity is classical, while the rest of fundamental physics is quantum. Usually this is not a problem. For an electron in an atom, gravity is so incredibly weak compared with the electromagnetic force that it can almost always be ignored. For a planet orbiting a star, quantum effects are usually far too tiny to matter. Each theory has its kingdom, and most of the time the border is quiet. But there are places where the border becomes unavoidable. Black holes are one of them. A black hole is a region where gravity is so strong that, beyond the event horizon, not even light can escape outward to distant space. General relativity describes black holes extremely well as curved space-time, but near the center, where the mathematics points toward a singularity, densities and curvatures become extreme. The theory appears to be saying that its own classical description has reached a limit. Quantum effects may become essential there. But a complete quantum theory of gravity is still missing. The earliest moments of the universe raise a similar problem. In the standard Big Bang model, the universe was once much hotter, denser, and smaller than it is today. General relativity helps describe the expansion of space. Quantum physics helps describe fields and particles. But if one tries to approach the very earliest era, when the entire observable universe may have been compressed into an unimaginably small and energetic state, both quantum effects and gravity should matter at the same time. That is exactly where current theory becomes incomplete. This broad, unresolved effort is called quantum gravity. Quantum gravity is not one single finished theory. It is the search for a framework that can reconcile quantum mechanics with general relativity. Two major research directions are string theory and loop quantum gravity. String theory suggests that fundamental entities may not be point-like particles, but tiny vibrating strings, with different vibrations corresponding to different particles. It also naturally includes a quantum description of gravity in certain mathematical settings. Loop quantum gravity takes a different route, attempting to quantize spacetime itself, so that geometry may have a discrete structure at the smallest scales. Neither approach has been confirmed as the final theory of nature. Both have produced important ideas, and both face major challenges. This is not a weakness to hide. It is the honest state of the frontier. Physics has two spectacularly successful theories, but not yet one complete framework that joins them under all conditions. One of the most famous bridges between quantum theory and gravity came from Stephen Hawking. In the 1970s, Hawking showed that when quantum field theory is applied near the event horizon of a black holes should not be perfectly black. They should emit a faint thermal radiation, now called Hawking radiation. Over immense timescales, this would allow black holes to lose mass. The idea is profound because it links quantum fields, gravity, thermodynamics, and black holes. It suggests that black holes have temperature and entropy, and it helped open the deep puzzle known as the black hole information problem. But direct observational confirmation of Hawking radiation from astrophysical black holes remains extremely difficult, because the predicted radiation is incredibly faint for large black holes. So the edge of the unknown is not empty, it is crowded with clues. Quantum physics has not failed because gravity remains hard. General relativity has not failed because quantum mechanics is necessary at small scales. Instead, science has reached a place where two excellent maps overlap imperfectly. Each map is reliable across a vast territory. The challenge is to understand what deeper landscape could make both of them true. That is a fitting place for quantum physics to leave us. Not with everything solved, but with a clearer view of what remains mysterious. It has explained the glow of hot matter, the structure of atoms, the behavior of light, the shape of chemistry, the power of modern technology, and the hidden rules beneath ordinary life. Yet at the smallest scales of space-time and the strongest edges of gravity, the universe still keeps part of its grammar unread. Not silent, not lawless, just not fully translated yet. Quantum physics can seem strange at first, but it is not strange because it is careless, mystical, or made from guesses. It is strange because careful experiments forced science to look beneath the smooth surface of ordinary life and accept that nature follows rules far subtler than common sense expected. It began with Max Planck and the quantum, the small packet of energy hidden inside the glow of hot matter. Albert Einstein showed that light itself could arrive in photons. Niels Bohr used quantum ideas to explain the stability of the atom and the coloured fingerprints of spectral lines. Louis de Broglie suggested that matter could have wave-like properties, and Erwin Schrödinger gave physics the wave function, a mathematical description of possibility. Werner Heisenberg revealed uncertainty not as clumsiness, but as a built-in limit of quantum systems. From there, the picture deepened. Tunneling showed that particles can sometimes appear beyond barriers that classical physics would forbid. Spin and the Pauli exclusion principle helped explain why atoms have structure, why matter has shape, and why the periodic table behaves as it does. Entanglement challenged the meaning of separateness. Quantum fields showed particles as excitations of something deeper. Quantum technology turned these ideas into lasers, transistors, atomic clocks, and the first careful steps toward quantum computers. And yet the ordinary world has not been taken away. A table is still solid, a star still shines, a ruby is still red, a screen still glows. Quantum physics does not replace familiar experience so much as explain the hidden machinery that allows it to exist. There are still open questions. Measurement, interpretation, and quantum gravity remain unfinished parts of the story. But that is not failure. It is the edge where science is still alive, still listening, still measuring. The world feels simple because countless quantum rules are working quietly beneath awareness with astonishing precision.